Okay, so I believe it's being recorded.
So won't it be live streamed as well, or will it be only recorded?
I believe so. The recording will certainly be uploaded, but I think it will. For now, it will be only recorded. I guess we're not able to see
Okay.
the live streaming.
Hello, sir.
Okay, so we can get started. Let me just share my screen. Okay, so how many of you are there from the previous term, right? So the previous term meaning the September term. Okay, is there anyone who is doing this workshop the second time? I know a couple of you, at least one of you. And is there anyone who is doing it the second time?
Yes, sir. I am doing it the second time.
Yes, sir. I'm also.
Okay.
Also, sir.
So see, the point is that this is going to be repetitive, right? So for those of you who are doing it the second time, this is going to be, I'll just do what happened last time, right? So it will be repetitive for you. So that's one heads up that I want to give you. And for the others, I am assuming the others are doing it the first time. So for you folks, those of you who are thinking about the certificate, right? So the certificate in MLT workshop is closely tied to the OPP, right? So in fact, it is only tied to the OPP. So just attending this, just logging the attendance here will not guarantee any certificate, right? So I hope that part is clear to you. Okay, so I'll just repeat this. If you want the certificate for this MLT implementing machine learning techniques workshop, then you'll have to attend this OPP that we'll conduct quite soon. I don't know when exactly, but you'll have to attend that and you have to pass that exam in order to get the certificate, right? So there is no participation certificate as such for attending this workshop, right? So just logging into the Zoom meeting, staying there for 2 hours will not give you a certificate, okay? Because I hope you understand why that is the case, right? So I just wanted.
Sir, can you please elaborate on the OPP, how it will be conducted?
That will come to the end. We'll discuss it towards the end, right? So that's
Okay.
It's like usual OPPs, right? Whatever you have for Java, Python, system commands, all these courses, right? So it'll be very similar to that. Only thing you will be coding things in NumPy, right? So that's the only difference.
So we will be notified about that later, right?
Yeah. You will be. So in fact, in order to be eligible, in order to become eligible for the OPP, you have to submit certain assignments based on this workshop. So only then will you be even eligible for the OPP, right? So and then you'll have to pass the OPP. But we'll like intimate you of all these things, so you don't need to.
Okay. Okay. Thank you, sir.
Okay, so yeah, for those of you who join new, if some of you are here from the previous term, meaning those who have done the workshop, who attended the workshop earlier, and you are attending this again, it will be repetitive for you. So that's just a warning that I'm giving right before we start. Okay, so.
Excuse me, sir. Sir.
Yeah.
Sir, so those of us who have already submitted assignment previously and were allowed to sit for the OPP, do we need to submit assignments again?
I am not very sure about that. I'll ask and get back to you. Is that right? I'm not sure.
Okay. Sure.
Sir, actually, I had completed my MLF in this term only, in the previous term, and I am planning to take MLT in the next term. So, shall I join this workshop?
It won't be actually relevant to you because I thought this form was sent only for those who have cleared MLT. Is that not correct? The only those who have completed MLT will like really understand what's happening. So
no, sir, they have sent four workshops together. So you can register whatever you want, like that it was sent.
All right.
So many of them were
There's no
not aware
option to
that
join with
MLT was
mail ID.
necessary to complete for this course.
Okay, okay. So yeah, see, this particular session may be relevant, but the next 3 days of the workshop will be hard without MLT, right? You need to know MLT to understand the next 3 days of the workshop. Today might be okay because we'll not be doing machine learning as such. We'll only be doing basic NumPy. So today is fine, but for the other 3 days, you need to know MLT to really appreciate what's going on. All right, so I hope we can start now.
Sir, 100% attendance is not needed for this workshop.
See, as I said before, this attendance is, we are not going to really do much to the attendance, right? So the attendance is not linked to the certificate. Okay,
Yes,
so the certificate is linked to the OPP, and this will be uploaded also. These sessions are going to be uploaded to YouTube, so you can watch them later. So I don't think attendance is so important.
So
Okay.
when will OPP be, like the date of the OPP?
We are not sure, right? We haven't decided. So
And sir, as I had not did MLT, but if I completed all these things, assignments and attend the sessions, then I will be eligible for OPP.
you will be eligible, but then you, so only if you do MLT, see, only if then MLT will this workshop make sense, right? I am just putting this out here. Without MLT, this will not make any sense.
Hello, sir. Last question. Regarding project, so can we start working on the project right away along with the along with this session, sir?
Projects, what projects?
There are MLP projects also there, right? MLP projects, sir. Machine learning projects are there. So there is a date like they mentioned, like it will start from the 10th May and the last date will be the 8th of August. The timeline is given. Probably, I think it is for them who takes the project in this with, along with MLP, I guess.
Yeah, so there is no project as such for this workshop. There is only
Okay.
set of assignments that you'll have to.
Okay, it's not related with the project, right? Okay.
I think so. I think so. Yeah.
Sir, what assignment we have to do in this?
We'll come to those things, right? So I will push them to the end of the session. Otherwise, it'll go in
Okay.
queries. So yeah, so let's get started. So we'll be looking at 3 libraries, broadly speaking. One is NumPy, and the other one is Matplotlib, and the third one is SciPy, right? So SciPy, we'll only touch upon it very briefly in the last session of this workshop. So that's why it's in smaller font. NumPy will be the most important thing. And of course, for plotting various things, we'll be taking the help of Matplotlib, right? So I'll just set the context for today's session. So we'll be looking at NumPy and Matplotlib. Okay, SciPy, we'll take it up on the last day. So NumPy, mainly we'll be looking at what vectors, matrices, how are they handled by NumPy, what are the facilities that NumPy provides to manipulate vectors and matrices, right? We'll also look at some of the concepts that we have studied in the machine learning techniques course and see how they can be applied using NumPy, right? So that's what we'll do with respect to NumPy. As far as Matplotlib is concerned, we see how we can plot very simple curves to begin with, and then we can go ahead and see how to plot various other things, right? So bar plots, histograms, scatter plots, contour and 3D plots, we look at it on Saturday, right? The last day. So that's the agenda. Now, what we'll do today is we'll go through a sequence of collabs, right? Collab notebooks. So we alternate between NumPy and some other library. In this case, it's Matplotlib. So the first collab will be exclusively discussing certain aspects of NumPy, and then we'll go and discuss some things related to Matplotlib, and then we'll come back to NumPy and so on, right? So that's the sequence in which we'll go. And mostly this will be some kind of a code with instructor session where I'll be coding. Now you can code along with me, or you can just watch me code, and then all these collabs along with the solutions are anyway going to be made available, right? So it's not mandatory that you should code along with me. Whichever is convenient, you can do that. So please make a note of this particular link. So tiny.cc/, MLT workshop that will take you to this particular folder. And if you go to day 1, you would see a list of collabs that we will be working with.
Sir, can you put the
So can
link?
you please?
Yes, yeah. I can paste it in chat. So tiny.cc/MLT_workshop. Okay, so I'll just wait for a minute for all of you to download or rather go to this particular page and open up the first collab.
Which collab, sir?
We'll start with 1, right? So the collabs are numbered this way. So we'll start with 1, and you can just keep it open. If you want to code along, you can keep it open. But otherwise, you can just watch what's happening, and later on you can. Right. So when you open it, what you will see is you can't edit it. So you will see this. And if you try to save it, it will show you that changes will not be saved. So you'll have to click on this copy to drive. Okay, so that will create a copy of this collab in your own system. So in your own drive, and then you can edit that particular document.
Good evening, Kartik sir.
Yes, yeah.
Can you explain one more time? Actually, just now I have joined. I had work actually. So just now I have joined. So can you explain a little bit so that I can understand? Just summary.
Yeah, so we have just started. So we'll be looking at these 3 libraries today, and we'll be going through 6 or 5 collabs. So 5 collab notebooks. These collab notebooks can be found in this link. So tiny.cc/MLT workshop. It is pasted in the chat. I'll paste it again. So you can all take a look at that particular folder. So it'll look like this. You go to that link, you'll find a bunch of notebooks. We'll go one by one. So we'll first look at this notebook. By the way, is everyone able to see the collab notebook when I shift the tab?
Yes, sir.
Okay.
Yeah.
Yes. Sir.
Okay.
Yes,
Right. So just give me a second. Right. So that is the basic idea. So that's what we'll be doing. Okay.
Yes,
So
sir.
I'll move on.
Thank you.
Yeah. So these 3, just a brief history of when these libraries were created. Okay. So these 3 libraries came into existence somewhere at the beginning of this millennium, right? So somewhere in 2000s is when NumPy, Matplotlib, and SciPy were created. So specific years are 2005, 2003, 2001, and all 3 are open source. That's a big advantage, right? So anyone can make use of it. Other developers can contribute to its source code. You can see exactly what happens. So that is a great advantage. So they're all in different versions, right? So those of you who have done MAD 1, MAD 2 kind of courses, you will know that there are different versioning systems, right? So this is like the 3rd version, Matplotlib, for example, and NumPy is in its version 1. Of course, several versions have gone before this. So our use for these, the way we will use these libraries is NumPy for linear algebra, okay, Matplotlib for visualizing things, data, models, the output of models, and all these things. SciPy, we will use it for optimization. Okay, so these are our use cases. I've not listed down what all you can do with NumPy, right? You can do hell a lot of things with NumPy, but we will be focusing on one specific aspect of NumPy, and that is manipulating vectors and matrices. Okay, so that's the overview. So I'll just give you a brief idea of why we should learn NumPy, right? So the question that some of you might be asking is NumPy still relevant, right? So why are we actually studying NumPy? And in the present day context, is it really meaningful to learn this library? Okay, so here is some survey that was conducted by Stack Overflow, right? So I hope most of you are aware of this website called Stack Overflow. It's a very popular website among programmers and those who are learning to code, and even experienced developers, very often go to Stack Overflow to get their doubts clarified, right? So Stack Overflow is a popular website. Now, every year they conduct surveys. So they ask developers and those who are learning to code several questions they asked. Okay? So last year, this is the result of the survey that was conducted last year. This year, it's actually going on. Okay, so this is the result of one particular survey. Okay, where respondents, the participants were asked to list down the most popular technologies, right? They were given a bunch of technologies and they were asked which of these do you think is most popular, or which of these do you tend to use? And you have two kinds of responses, right? If you notice, around 40,000, 41,000 responses are there from professional developers, right? Those who are working in companies, those who are developing software, those who are data scientists, right? All of them responded. And you can see that around 24% of them have chosen NumPy, right? So, and that's like the second in the list. So you can see that among developers, NumPy is quite popular. So the link is here. You can, I'll share this set of slides so you can go through it later. Now, for the other bar is this one. Those who are learning to code, you can see that NumPy is the most popular from a set of libraries and tools, right? So Pandas comes very close by. sklearn, which you learn about in the MLP course next term, that is also quite popular. But you can see that as far as learners are concerned, NumPy is extremely popular, and this is like around 4,000 responses, much less than the 40,000 odd responses here, but it still shows that NumPy is one of the most popular technologies and it is still relevant. Okay, so there's one more interesting result of the survey where they look at these frameworks and libraries and see which of them are top paying, right? So what is the pay package in some sense, or how much money is associated with it? And if you notice, NumPy is not there at the top, but still it's pretty much relevant, right? About 66,000 USD is what is tied to NumPy. And what you see at the top are some big data related libraries. So they are, of course, much more relevant, but NumPy is not irrelevant, right? So it is also in some sense relevant. Yeah, any questions? If someone has raised their hand.
Yes, sir. Please also highlight the difference between NumPy and Pandas.
Okay, so NumPy is more of, so as the name suggests, NumPy means numerical Python, right? So it's in some sense, it's a very low level language, low level in the sense you deal much more closer with you're at much closer, interaction with the data, right? So it is at that level. Pandas is one level higher than NumPy, right? So it's in a sense more powerful in certain applications. So you can take the whole data set, you can do a lot of things with it, right? So we'll come to the Pandas aspect later, but for now, let's focus on NumPy. Is that fine?
Yes, thank you.
Yeah, so someone else raised their hands. Any other questions?
Sir, as you said, okay, there is a lot of use in NumPy compared to scikit-learn, but in scikit-learn there are a lot of libraries are available. Whether same libraries I can able to do through NumPy, or I have to write the code for those specific libraries functions.
Okay, so sklearn is built using NumPy, right? At some level, not only NumPy, but NumPy is like it fits into sklearn, right? So there are many modules in sklearn which are obviously not there in NumPy because sklearn is the purpose of sklearn is different from NumPy, right? So NumPy, as I said, is much more closer to the mathematics side of things, if I may put it that way, right? And sklearn, you could say, is much more closer to the application side of things.
Yeah, only NumPy will not help us. Together, NumPy.
Yeah, you are right. Correct. I agree. Yeah. Only NumPy is not going to help us. You need to know. NumPy is important to know. It's like necessary to know, but it's not sufficient, right? So if you bring in the question of is it sufficient? No, right? So you need to learn. You certainly need to know Pandas. You certainly need to know sklearn, and only then will the whole thing be complete. But what these set of slides are showing is that NumPy is relevant, right? It's necessary. It's not showing that it is sufficient.
Okay.
Okay. So yeah, that's the introduction. So again, I just spend
How to get the slides?
very, yeah.
How to get the slides?
Slides, I'll share it later.
Okay.
Sir, I have one more question. What is the difference between SciPy and sklearn?
So see, these are all different libraries, right? sklearn has got more to do with the machine learning side of things, whereas SciPy is slightly more general purpose where you can do a few other things. But for now, why don't we concentrate on NumPy, right? So we'll learn NumPy a bit, and then we'll see what other libraries can offer. Okay, so yeah, so I'll shift to the collab in a minute. Before that, I just want to set the context about why we are so interested in NumPy from the ML point of view. So this slide, some of you might have seen during the MLT course. So we are looking at vectors, right? So everything that we do is with vectors and matrices in machine learning. So a data point or a sample or an example is a vector, right? And here there are only two features, okay, for my data point or my sample, but then you get the idea, right? So there could be 10 features, then this will be a vector in 10 dimensional space, right? So this is the practical side of things. You get data, each training data point is a vector. Okay, so from there you go to the idea of an abstract vector space, right? So you look at these vectors residing in some vector space, and then you can think of them as geometric and algebraic objects. You can add vectors, you can take the dot product, you can do all these things. Okay, so which is what actually gives rise to most of the ML algorithms, right? So we do a lot of these operations and in our ML algorithms. So how do we translate all this into something that our machines can understand? That's where NumPy comes, right? So NumPy is also going to deal with vectors, but then it will deal with them by this object called a NumPy array. Okay, so that's what we'll be focusing on from now on. Okay, so shall we start the coding part?
Yes, sir.
Okay, so yeah.
Yes, sir.
Yes, sir.
First, go ahead and import NumPy. So it's a simple import. Import NumPy as. Okay, so this is.
Sir, we can also do parallelly in the collab you send us.
Yeah, you can, but you'll have to make a copy of it. Okay, right. So once you do that, what will happen is you now have imported NumPy, right? So that's the first line of code that we have written. We have imported the library. So now let's take a look at some vectors, right? We have two vectors, x and y, and we can add these vectors as you all know, right? So first, let's go ahead and do this using traditional lists, right? So this is a list, right? X is a list. You can treat this as a vector, and y is 4, 5, 6. So you can also treat this as a vector. Okay, this is what you would do if you didn't know NumPy. Your first approach would be to treat a vector, a mathematical vector, as a list of numbers. Okay, so that's what you would do. Now, how will you add these vectors in native Python without using NumPy? How will you add these two vectors? Can someone tell me?
Yes, sir. For I in the range
Using loops.
Okay, using loops, right? So let's do that. I just make sure that I have defined my number of elements. So there are like length elements, right? So for I in range of n, what I'm going to do is I'm going to append something to z. What will I append?
xi plus yi.
X of I plus y of I, right? So this is what I'll append. And if I run this collab, so by the way, if you want to run this collab, you can do two things. You can either go ahead and click on the run cell, or you can do control enter, right? So if you do control enter, that will run the collab, the cell for you, right? So each of these things is called a cell. So this is a cell, this is a cell, okay? And you can run the cell, you end up with 579. Okay, so this is what you wanted, right? So x plus y equal to z. So this is using native Python. Now let's see how this is done using NumPy, right? So what NumPy does is, first we have to create what is called a NumPy array. Okay, so NumPy array will be This is the syntax for a NumPy array. So x equal to np dot array of, you put in the list of numbers, that is your vector. Okay, so let's see what that is, what that comes out to be. Okay, so this is what you'll get as output, array of 1, 2, 3. Okay, you can now check for the type of x, what kind of an object is x. It will show you that it's something called an ND array. Okay, so it's called a ND array. I'll come to what the ND part means later on, but this is what is called a NumPy array. Okay, so let's now define y, another NumPy array. Okay, another vector, 4, 5, 6, right? That's the next vector. So if you just type the variable and run the cell, it will show you what that variable is. Okay, so if you type the variable, if that's the last line in your cell, and if you run the cell, it will just give you whatever is there in that variable. Okay, so you don't need to necessarily do print of y. If you do print of y, you will end up getting 4, 5, 6. But a shortcut in Colab is you can just list down the name of the variable, and that will give you what you're looking for. Okay, so that is x and y. And if you want to add these two vectors in NumPy, it's as simple as this. Okay, so notice the difference in syntax for addition of two vectors using Python lists and using NumPy arrays. Okay, so you see what is great about NumPy is that it's very similar to the way you would do math, right? So notice this expression, right? Z equal to x plus y. That's exactly what we have written down, but in terms of variables, right? Programmatically, we have written this down. It very closely resembles the mathematical aspect of vector addition. Okay, so that's the great advantage of using NumPy, or one of the great advantages. We'll of course see several others, but I hope you all are clear about how simple vector addition works using NumPy. Any questions about this? Okay, so let's thanks. Yeah, let's move on now.
Sir, if the number of elements are different, will it work similarly?
It won't, right? So let's try that. If the vectors are of different dimensions, let's say this is 4, 5, 6, 7, and that is 1, 2, 3. If you try to add them, it will give you the following error, right? So we'll come to this broadcasting part. It says that operands could not be broadcast together with shapes 3 and 4. Basically, this has shape 3, this has shape 4, meaning 4 elements and 3 elements. So they could not be added together, right? So you'll get an error. So addition will happen only if they have compatible dimensions, right?
Sir, one more question. Sir, in this case, for example, array, if I want to enter the values, for example, in this case, you have taken 1, 2, 3. Now I don't know the value. I'm entering the value from the user. So in that case, I have to use a loop. For example, in Python, normally what we do.
Yeah, you would have to do that. Yeah,
okay.
But usually, right? So I mean that you will already know what these vectors are, right? So but for your situation, yes, you'll have to use a loop, get the values, and then form the array.
Okay, fine, sir.
Okay, so that is NumPy, that is addition, vector addition, right? So, okay, so actually I should have written this here. Okay, that was meant to be here anyway.
No, sir, one more cell down.
Yes, yeah. Yeah, go on. I just have to copy certain things. Yeah, go on. Yeah, you had a question?
Sir, can I ask a question? I'm sorry if you not answer.
What was that, sir? 1x?
Which one?
This
it's a line number, right? So this is not
acha. Okay.
Okay, so that's the line number. Yeah, so that is.
Sir, for x, when you put np dot array, that array number of elements is only 1, sir. For the x, you put np dot array 1, 2, 3. So that array, the length of array is only 1.
The length of the array will be the length of the number of elements, right? So, for example, if I type length of z, you will get the value as 3, right? Because there are 3 components to this vector.
No, I thought like that is within those 3 elements are within one list. So an array is a list of like list of lists. So I thought array number of elements in for X, so it will show as only one, I thought.
No, right. So you are right in saying that X is one object, right? X is one object, but then that object internally has 3 components associated with it, just like a vector, right? So we call this vector X. X is only one object, but then it has 3 components associated with it, right? X of 0, X of 1, and X of 2.
Okay, sir.
Sir, I have a question here. Can
Yeah.
I?
Yes, yeah.
Sir, since this array has 3 elements, because it is when you type length of the X, so that gives us 3. So if array is too big, suppose 100 elements are there, then what we have to do? It's because it is np.array, you have written the array 1 to 3, right? That will be difficult for us to type the whole array, right? Then what we will do?
Yeah, so typically you will store these arrays in a certain format, right? So you'll be storing them as files. You'll be reading from these files, processing them, right? So you won't be manually entering one by one every time.
Can I answer that?
I guess we can use like list comprehension for like
Can I answer
100
that?
numbers. So can we use?
See, if list comprehension only if you know that they are in a sequence, right? So, for example, if you have a data set, so data set will typically come to you in the form of, say, a file, right? It's a CSV file. So if you have a CSV file, you can just load it into your system and as a NumPy array, so that you'll load the CSV file itself as an array.
Hello.
Yeah, go on, Mosu. Yeah.
Yeah, no, I just wanted to answer that. Typically, the data is in some Excel or CSV file, or you pull it out of SQL. Then you use pandas to first read the data, just to understand, how many rows are there, what are the columns, right? Some basic analysis to understand the data. After that, whatever you're doing further, you typically from pandas is like an Excel. Think of it in Excel in Python, right? So it has columns and rows. Then you convert that into a NumPy array. There is a simple command, to NumPy array, to array, NP array. That's it. It gets converted to an array. You don't physically ever type any of it. It's not possible. Very simple. It's half a second.
Yeah, understood. Yeah, I got it.
Sir, please continue.
Excuse me, sir.
Yeah.
Can I please suggest something?
Yeah.
Please have questions a bit later rather than having it every time, because
sure, yeah, I think that makes sense. Yeah, so I'll maybe stop at the end of
you have just done the 2 cells and you have just gone away.
Right, yeah, okay, we'll do that. Okay, so the next thing is we looked at vector addition, right? So next thing we'll do is element wise multiplication, right? So what happens if you multiply 2 vectors together? So element wise, so for example, if you have X as 1, 2, 3, Y as 4, 5, 6, right? What happens when you multiply X and Y element wise? So 1 will be multiplied with 4, 2 with 5, 3 with 6, right? So I hope you get it. This is called the Hadamard product. So name is not important. What is important is how do we do this using NumPy, right? So NumPy offers a very neat way of doing this. Okay, so I've defined these 2 vectors. All that you need to do is, just like your usual multiplication, you just need to do X star Y. Okay, so when you do X star Y, what happens is NumPy treats that as an element wise operation. Okay, so there's a few technical things here which we'll not touch into. We'll come to that later. But if you use the star operator, please remember that the operation will happen element wise. This is exactly what happened for addition also, though we didn't mention it. Addition for vectors happens element wise, right? 1 is added with 4, 2 is added with 5, 3 with 6, right? So exactly the same thing happens with the star operator also. Okay, so that is element wise multiplication. Let's now look at the other important operation that we do with vectors, right? So we scale vectors. Often we have to multiply a vector by a constant, right? So let's do that here. So if you have a vector like this and you want to say scale it with some constant, let's say 3, what do? You just do y equal to 3 star x, right? Again, the same star comes in here. Okay, now let's see what y is. It's just scaled by a factor of 3, right? So how does NumPy know that this has to happen element wise? Okay, how does NumPy know this? It has something called something known as broadcasting, right? There's a concept called broadcasting. So I'll just very quickly touch upon that. We won't go into the details of broadcasting because it's slightly complicated for the beginning stage, right? So this is a NumPy array, right? So you're all clear about what an array is. So I'm multiplying this array by a scalar 2. That's what we are doing. So here in this case, we are scaling it by 3, but assume that we are scaling it by 2. So how does NumPy know that it has to multiply this element wise? Internally, it does what is called as broadcasting. So what broadcasting does is, again, is a very crude way of putting it. It stretches this scalar 2 along the axis of the original vector, right? So the original vector is what, 1, 2, 3. Okay, it has 3 components. So if you think about multiplying by a scalar as creating a new array, right? Creating a new array, okay, where every element is 2. Now you can multiply these 2 element wise to end up with 2, 4, 6. Okay, so this principle is called broadcasting. You can think about broadcasting as some kind of extension that you do to a particular array so that the operation that you want to do becomes compatible. Okay, so what I mean by that, here you have an array of size 3. Okay, here you have an array of size 3. Here you have a scalar. Okay, and they are not really compatible, right? If you think about it in one sense. So if you want to make them compatible for multiplication element wise, you broadcast this 2 so that you can do this kind of element wise operation. Okay, I'm not sure if I expressed myself clearly, but it's just for now, you can, even if you didn't understand what broadcasting means, it's fine. Syntactically, if you understand this, it's enough. So what you're doing is, if you want to scale a vector by some constant k, just multiply, just use the normal star operator and that will scale the vector. Okay, so we'll get back to this broadcasting a few collabs later. So for now, I'll move on. So again, there's a lot of symbols here. So what I'm saying here is very simple. Suppose you want to, let's forget about all this text. Okay, just go to this example. Let's say you have a NumPy array made up of these 4 numbers, right? It's a vector of size 4, 1, 2, 3, 4, and you want to square each element. So you want the output to be 1, 4, 9, and 16. Okay, how do you do that? So typically in Python, what do? You have 1, 2, 3, 4, and you want to produce a new vector which has the square of the elements of the old vector. You again use the usual loop, right? So for I in range of 4, y dot append x of I square. Okay, that's what you do. And then if you execute this, you will end up with 1, 4, 9, 16. Right? So this is what we typically do in native Python. NumPy thankfully has a nice way of doing this. So you create as usual, you create a vector, a NumPy array out of this. And all that you need to do is, as though you are multiplying a single number, a scalar value, you can just type y equal to x square. And that will give you what you're looking for, right? So notice that x is actually a vector. Okay, x is actually a vector. But what we have done is, in some sense, we have used the star operator, the exponentiation operator on a vector, and that did an element wise squaring. Okay, so this is the important point. So element wise squaring. This is what I have given down here, right? So if you want to do some element wise, you want to apply an element wise function on every component of a vector, then you can do it very simply using something like this in NumPy. Okay, so any questions about these examples so far?
No, sir.
Okay, so let's move on. Let's take a slightly more complex function than the square. Let's do it for log. Okay, so you have this particular array made up of powers of 10. Okay, so let me type it out. So you have 1, 10, 100, 1000, 10,000, and 100,000. Okay, so by the way, one neat trick in Python is the use of this underscore, right? So the underscore is like a placeholder. It kind of it's a placeholder for separating numbers, right? So the way we will write 1000 as 1,1000, right? 1,3 zeros. So it's something like that, right? So it doesn't change the numerical value. It improves the readability of the code. Okay, so this is the NumPy array. Let's just see what we have here. Now we have to apply this log function on each of the elements of the NumPy array. In very simple, so you just do np.log of x. Okay, there is a small catch here. Log by default gives you the natural logarithm, right? So it gives you natural logarithm element wise, as this says. So you want log to the base 10, so you use log 10. Okay, so if you do that, you get the corresponding logarithm, right? So that is what you do. Now let's take the case of one more array where instead of powers of 10, you have powers of e, right? So how do you do that? Let's first define this array, np.array of 1 np.e. So e, by the way, can be expressed as np.e. So the two popular constants are pi and e, right, which you keep seeing. So np.e and np.pi are, that's the command or syntax for them. So np.e cube, right? np.e cube is, this is what you have. And now you can use the natural logarithm. So if you do np.log of x, you end up with 0, 1, 2, 3. Okay, this is the ln of x applied element wise. All right, so I'll just very quickly do these two examples also. Now, what happens if you want to add a constant to each element of a NumPy array? You might want to do it, right? Sometimes. So you want to add a constant to each element of an array. So again, that's quite simple. Just like what we have been seeing so far.
So can you just go up for a second? Sorry, I just just okay, got it. Thank you. Thank you.
Yeah, so this is what it is, right? So you just define the array and then you add c as though x were a scalar, right? So x is actually a vector. Please always remember this. C kind of gets broadcasted across all the components of x. Okay, do not forget that x is a vector. X is a vector and c is a scalar here. Even though that is the case, when you do x plus c, c gets added to each element of x element wise. Okay, so that's the catch. So again, I'll keep stressing this point. Look at the neat transition from mathematical symbols to variables, right? So if you want to do x plus c, that's exactly what you do here. Okay, that's the transition from math to programming, and NumPy makes it very easy. Okay. Now, one last example before we move on to other things. What about something like this, right? You have 5 times a vector minus 2. So when you say 5 times a vector, so this should be applied element wise again, right? So how do you do that? Again, let's first define the vector minus 1, 0, 1, 2. Now it's as simple as 5 times x. Okay, 5 times x will scale every element of x element wise and then subtract 2 from each component and you get the result. Okay, so math to NumPy, smooth transition. Okay, so that is these are like 4 examples that show you how you can apply a function to each element of a NumPy array as though you are treating this x as a scalar value, right? So that's what these 4 examples have shown you. Okay, I'll just pause for a moment. Any questions at this stage?
Sir, I have. Sir, regarding broadcast.
Okay.
Sir, can you go to the previous question where we add a constant?
Okay.
Sir, here we add c is equal to 5 to every element of a vector.
Right.
Suppose instead of 5, if we want to add 1, 2, 3 in sequence, in first element we want to add 1, second element we want to add 2, and third element we want to add 3.
Okay.
Can we do it? And how we can do it in
You just
NumPy?
scale it by 2, right? So you can just do 2 into x, right? If you want to add itself, you want to add the vector itself to x, you can just do 2 into x, right?
So if some number that is not a multiple of any number, here we have 5, but if we want to add a different numbers.
So that will just be a different array.
Correct. Yeah, you will
Adding.
just in a different array and add those 2 arrays.
Suppose here, so here we have 3 numbers, three elements in this vector, and if there are 4 and we want to add 1, 5, 1, 5. Is there any way?
I mean, yeah, if you want to add another vector, you can always add, right? So you can define y equal to np dot array. I don't know what you want to add, but if you want to add 1, 5, 1, then you can just do x plus y, right?
No. Sir, in the first line, we have 1, 2, 3.
Okay.
Suppose we have 1, 2, 3, and 4.
Okay.
And the constant, we have constant 5. And instead of one constant, I want to add 5, 1, 5, 1.
That's what we said, right? So why do you want to think about it that way? Just think about it as another array, right? So that's all right. You will add x plus y now. You want to add some things to x, right? So you just add another vector to x.
I was thinking in terms of broadcasting. We have only one element that we were broadcasting. Suppose we have 2 elements that we want to broadcast alternatively.
Okay. That's a bit tough. So this broadcasting, I will not touch upon it in great detail because first thing, I myself don't know a lot about broadcasting. I'll only use broadcasting in a very I'll introduce broadcasting in a very specific sense, right? So beyond that, it will be confusing for an introductory workshop on NumPy. Okay, so
sir, I have a question. Can you go to that log fx equal to log x?
Okay, so after this question, I'll move on. Okay, so I'll then take the next question later. Yeah.
Yeah. Log files. Yeah. In that you have written in underscore 1 underscore 1000. It is 10,000 like that, right? Underscore.
Correct. Underscore just improves the readability, right? So you can remove that also, but it will work the same.
Okay. Fine, sir.
Okay. Right. So
could you just show example 4?
Okay, so what I'll do is I have just few more cells. I'll finish this collab and then you can ask the questions. Right?
Sir, I'm asking about how to get the YouTube link.
I am not sure, right? So let's put all those to the end, right? So the YouTube link will be up, right? It will be session is being recorded. So I hope it is being recorded.
It's already been 48 minutes. Please continue.
Yeah, I think it's being recorded. So
yes,
we'll make sure that it's uploaded, right? So we'll go to the dot product and then I'll take one more set of questions. Okay, so dot product is very familiar to all of you and it's the most important operation in all of MLT, right? So let's see how it's done. I'll just use the vectors given here. Okay, so if you want the dot product, there are multiple ways to do it in NumPy, right? One is to use a function called np.dot, right? So if you do np.dot of a comma b, okay, so as you can see, if both a and b are 1D arrays, I'll come to what 1D is. It will give you the inner product or dot product of the two vectors, right? So let's do that and see what we get. You can verify that this is the dot product, right? So you'll get this actually. Now, there's a simpler way to do it using what is called the @ operator in Python. It does the same thing. Okay, it gives you the dot product of x and y. It's much more simpler and easier to parse compared to the np.dot. It's not wrong if you use np.dot, but then x at y is much more easier to remember than np.dot. We'll also see y at matters very soon, right? So we'll see why it matters soon. So this is the dot product between two vectors. Now, you might remember certain occasions in the course where we used vectors of ones, right? For example, in the week on SVM, we had this vector of ones that we defined, right? So these vectors are very useful. So how do we create a vector where all of the elements are either zeros or ones? Okay, so it's a very simple command to do that. It's called np.zeros. You just need to specify how many elements or components your vector should have. In this case, there are 5. Okay, that will give you a vector of size 5. Okay, and if you want a vector of size or a vector of ones of size 5, this is how you'll do it, right? It's np.zeros and np.ones. Now, what if you wanted to create a vector where every element is equal to 5? How do you think we'll do that?
Sir, we can run for loop inside the list of the NP array.
Scale np.ones.
Okay, we just scale np.ones, right? That's the easiest way by 5. Okay, so you already know how scaling works, right? Scaling works element wise, and all that we need to do is get hold of a vector of ones multiplied by 5. Okay, so that's all we need to do. So this is how you create vectors of zeros and ones in NumPy. Okay, useful command will come in handy. So sometimes what we may want to do is create a list of integers, okay, which are in a particular sequence. Okay, so this, as you all know, in Python, we can do it like this, right? So you have range of 1 to 6. And if you want to create a list of these numbers, you have 1, 2, 3, 4, 5, right? So this is what you do in native Python. You could, of course, wrap np.array around this. Okay, that will give you a NumPy array from 1 to 5. Okay, you can do this. Thankfully, NumPy provides a way to do this without having to go via Python. So np.arange. Okay, so you just need to remember that instead of range in Python, in NumPy it is arange. Okay, so starting and the initial point will be included, the endpoint -1 will be included, right? Similar to how the range function in Python works, it is arange for NumPy. So NumPy.arange of 1 to 6 will give you this. Okay.
Sir, does it mean that 1, 6, 2 will it give? Does it act like that as well?
I think so. Let's just try that out. Yes, right. So it acts very similar to your range function in NumPy.
So
okay.
in case of decrement order, if I wanted to do
that also will work, right? So let's do 6, 1, -1. So that will go from 6 to 1, taking one step decrement.
Okay, sir.
Okay, so yeah, these are useful questions. So please make a note of these two responses and questions, right? They were useful. So what is the norm of a vector? So norm of a vector, as you all know, again, we used it so many times in MLT and also in MLF, right? NumPy.array, this is the vector 1, 2, 3. Now what you can do, so here is something that you can do, right? L2 norm is what? You want to find the sum of the squares of all the components of the vector and take the square root. So what you can do is, you can do something like this, right? You can do x square. So let's first do x square and see what we get. We get 149. Okay, and then you can sum this. So you will get 14, and then you can raise the whole thing to the power half, right? So you can do this. Okay, very roundabout way of doing it, but still it works, right? So it works. Alternatively, what you can do is NumPy provides a nice utility for this. So NumPy, inside NumPy, you have a module called linealg. Linealg stands for linear algebra. So np.linealg.norm of x. That will also give you the same thing. Okay, so this is the L2 norm of x. Okay, L2 norm of x. Suppose you want the L1 norm, all you need to do is specify the norm that you want, right? Here it's L1, so it will give you the L1 norm. You need to type in this 1 here. Okay, so the default argument, the second argument is the p value, right? If you recall, we studied about LP norms, right? So there are a whole range of norms that you can define, and L1 and L2 are two such norms. So if you want LP norm in general, you have to type in the value of p here. By default, if nothing is specified, it will be the L2 norm. So you can, if you want the Euclidean distance or the L2 norm, you can just drop the 2 and it is going to give you the same value. Okay, so that is the norm. It's a very useful module, np.lineage. We'll come back to this, some module inside NumPy. Very useful for linear algebra operations, as we'll see. Okay, so this is the last point, and then I'll take two questions, and then we'll move to the next collab. So vectors are one-dimensional arrays. Okay, so you must not confuse. So don't read what I've written here. So I'll just listen to what I'm saying. So vectors are single-dimensional NumPy arrays. Okay, so you're all used to the idea of the dimension of a vector being the number of components it has. Okay, so that is the vector space dimension, right? So X here belongs to R4, right? So there are 4 components, 1, 2, 3, 4. So the vector space dimension is 4. There's no change in that. So if I type down 1, 2, 3, 4 and ask what is the length of X, it will give you 4, right? So it has 4 components, 4-dimensional vector. So there is no change in that. But when it comes to NumPy, there is something called the NumPy dimension. Okay, so if you type in this ndim, right, you get the result as 1. Okay, so why is this the case? It will become clear when we discuss matrices, okay, in the next collab. But vectors are single-dimensional NumPy arrays. So this is what you have to remember for now. Matrices are 2-dimensional NumPy arrays. We'll discuss that next. But for now, note that there are 2 dimensions that are involved. One is the usual vector space idea of dimension. The other one is the NumPy dimension or ndim. Okay, so before we move to the next collab, are there any questions?
Sir, can you go to norm portion? Where? Yeah, here it is what you told that if I need to find the L2 norm, then x comma 2 we have to put, right?
Yeah, x comma 2.
And if I go, and in which case we need to put the p?
If you are, for instance, calculating some other norm, so usually you will only use L1 and L2, right? So, but you might have a need for other kind of norms, right? So, for example, there is something called the L infinity norm that is also used sometimes. So, in such a case, you will have to use a different value of p.
Okay, it might be any values.
It might be, it depends on the application, right? Usually, it's only L1 and L2 that we require.
Okay, fine. Okay, thank you.
Okay, any
sir?
Yeah, one question, sir, on the dimension and so here NP array. See if you do x dot shape, you get 4. That is probably that's the dimension of the vector space or whatever. It's a 4D vector. Here, when we do x ndim, you get 1. What is that? The columns basically. Is that how best way to remember number of columns in the array?
So we'll come to, yeah, this will become more clear when we do
okay.
Sir, can you take a array of 2 dimensions?
We'll come to that. That's the next collab, right? So yeah, the shape, thanks for remaining. Shape I have to mention, right? So x dot shape will give you the shape, right? So you can see already there's one comma, right? This comma is actually a tuple. So this is actually a tuple, right? So if you look at what the type of this object is, you will notice that, you'll notice that x dot shape returns a tuple. Okay, so meaning that there are multiple elements that could be included, right? In this case, it's just a tuple of size 1. There's only one element because there's only one dimension. But if you have other kinds of NumPy arrays, you'll have more dimensions. We'll come to this dimension part very soon. Okay, so that is collab 1. Let me open up collapse number 2.
Please share the collapse.
Collapse are already shared. In fact, they would have been updated by now with the whatever code I have typed. You have to refresh and see, you will see that the changes have been updated.
Okay.
Okay, so before we go to matplotlib, I'll just this slide is there, right? So this is just a short kind of a cheat sheet for going from math to NumPy, right? So if you want to add two vectors, what is the mathematical expression and what is the corresponding NumPy expression, and you will see how simple it is to translate from math to NumPy. Okay, so we just saw all of this, right? If you want element wise product, it's x star y. If you want dot product, it's x at y. The rest of the things look very similar, right? So if you want the LP norm, it is this. Okay, so this is something we have already looked at. Now we'll go ahead and start plotting.
Hello.
Yeah.
Sir, I wanted to ask, what's the default value of p in that norm function?
That is 2, right? It is 2.
Okay.
Okay, so NumPy has NP, right? So we already know how to import NumPy. Okay, that we have seen. Now what we'll do is we'll import matplotlib .pyplot, right? Pyplot is one of the modules inside matplotlib as PLT, right? So you don't need to know exactly what pyplot is and all that. This is like some kind of you can treat this as something that's by default done by everyone who uses matplotlib, right? So for now, just go with this. We'll basically be using PLT to do all plotting, right? Any plot that we want to make, we'll be using PLT. Okay, so the first thing is, let's look at how we generally plot things, right? So if you want to plot a curve, y versus x, what we typically do, right? So if you go back to your school days, what you used to do was you'll take some, say, finite number of values of x, right? So you'll maybe take intervals of 1, say at 0, what is the value of y, and x equal to 1, what is the value of y? You'll put a dot, right? So you'll put a dot on your graph sheet, and then using a freehand or smooth curve, you will try to join all these dots. Okay, that's how you will, if you remember, that's how you would have plotted very simple graphs in school days, right? During your school days. So you can think of matplotlib doing something similar when it's trying to plot curves. So that's what we'll do. So the first thing that you need to have is a set of x values, right? I want to plot y versus x. So I need a bunch of x values, only then I can compute the corresponding y values and then plot y versus x. Okay, so how do we get hold of these x values? That's where we get this idea called linspace. Okay, so linspace, what it does is, it takes an interval. So in this case, the interval is 0, 1, and it divides it into an equal number of points. In this case, I want to divide it into 3 points, or rather I want to have 3 samples in this interval 0 to 1. So if I run this command, what I get is the point 0, the point 0.5, and the point 1. Okay, so let's do this once. And then if you do more examples, it will become clear. So this is what we get, right? So I am dividing the line segment 0, 1 into 2 equal parts. Okay, that's what I have done here. Into 2 equal parts, but in terms of the number of points that I get from it, I get 3 points. I get 0, 0.5, and 1. Let's do 4 points now. I want to get 4 samples from the same interval. Then what linspace will do is, it will divide the line segment into 3 equal parts, right? 1/3, 1/3, 1/3. And that will give me 4 points, 0, 0.33, 0.66, and 1. Okay, so you can try this out and you will see that exactly that's what happens. You can keep going on and on, right? So let's just do 2 more examples. So if you want to divide it into 4 equal parts, or if you want 5 samples from this 0 to 1, this is how you do it. And if you want 6, This is how you do it. Okay, so it's the idea of np dot linspace 0, 1 clear what we are doing? Because if you don't understand this, the rest of the cells will not be clear.
So this returns an NumPy array.
Yeah, yeah, exactly. This returns
Evenly distributed.
Yeah, evenly distributed set of points. Endpoints are included. That's the only catch. So if you say 0, 1, both 0 and 1 will be included. The 6 corresponds to the size of the array. So if you want, you can check this. You run x.shape. shape. You'll see that it has 6 components. Right? So it gives you 6 points which are evenly spaced between start and end point. So start here is 0, end is 1. You could, of course, try different start and end points, say 10 and 20. That will give you a different set of 6 points, right? But the idea is essentially the idea is the same. Okay, so I'm moving on. So that's how you partition the real life. Okay, so wherever you want to plot, you have no marked of the x values. You need to mark the corresponding y values. So let's first try to plot the line y equal to x, right? So this is what the question says. Sample 10 equally spaced points in the interval. So how do what's the command for that from what you've seen so far? Can anyone tell me what you will use here?
np dot line space 0, 1, 10.
Correct, right? So this is what you'll use. So you have now 10 equally spaced points between 0 and 1, endpoints inclusive. Now, corresponding to that, you need to create the y values, right? In this case, it's very simple, y equal to x. So y and x will actually be the same. Strictly speaking, you don't need a new variable, but for the sake of completeness, I'm adding it. Now you have to plot it, right? You have to plot it. So it's a very simple function, plt.plot the x values and the corresponding y values. Okay, so if you plot them, this is what you get. So what NumPy does, what matplotlib does internally is it does this joining the lines, right? Using a straight line. So that's what it is doing actually. Between 0 and so if you want to see the points, you also want to see the points, you have to do what is called a scatter plot, right? So x and y, if you want to see the points along with the line, this is how it looks like. Okay, so I'll now comment out the plot and show you what the scatter alone looks like. This is what the scatter looks like, right? So remember what I told about the school days plotting. So you just first you plot 0, 0, then you plot 0.1, 0.1, 0.2, 0.2, right? And then what you do is you draw a line, straight line through all these points. Okay, so that's what internally matplotlib is doing when it calls plt.plot of x, y. Okay, so that is how you plot simple curves. So see, if you don't want this is actually the output of the last command that is there here, right? So if you want to suppress this, so if you want to suppress unwanted output like this, you have to add a semicolon. Okay, it's a tip that you can use. If you don't use the semicolon, this thing gets printed. Sometimes it will be irritating to see some things like this, right? So I usually use the semicolon to make sure that the output is suppressed.
Excuse me, sir.
Yeah.
So I'm getting an error like module matplotlib has no attribute plot.
Okay, so did you import it like this? You have to import. You should not just import matplotlib. You have to import the module pyplot and call it plt.
Okay, sir.
Okay, so suppress unwanted outputs, use semicolon. Okay, so that is simple line. Okay, now let's plot 5 minus 3x.
I'm sorry, I didn't understand what you mean by suppress unwanted output.
Okay, so this assume that the semicolon is not there. Okay, so the semicolon is not there. I'm getting this line, right? Matplotlib.collections.path collection, whatever. So this is the output of the last line in your cell. The last line in your cell is plt dot scatter. So if you actually print, this has a, so this is actually a function, right? So this is going to have a return value. So plt dot scatter, when you call it, it's going to return some value. And if you print that value, it's actually this. Okay, so that gets printed. Now, I don't want that I don't want that to get printed. Therefore, I add the semicolon.
I got it.
Okay, so yeah, so can someone tell me how we will plot 5 minus 3x? What will be the first line of code?
Sir,
First stage x is equals to
minus 5
minus 5 to 520.
20.
Okay.
Y is
Y
equals
is
to
equals to
5
5 minus
minus
3x.
5 minus 3x.
Okay, 1 second. 5 minus 3.
PLT dot plot y.
Okay, PLT dot. Okay, again, I want to suppress the output, so let me just add. So we have plotted this particular line, and just for completeness sake, I want to know where my dots are, right? The dots that were used to plot the line. So I'm adding this plt dot scatter also, right? So I get this. Now that looks nice. So we are asked to do something more, right? We have to add a title to the plot, which has the equation of the curve. So let's go ahead and add a title. It's actually this particular command. So matplotlib and NumPy, they are very intuitive, right? So the methods that are available are not very hard. So plt.title y equal to 5 minus 3 times x. Okay, let's run this and notice that you have the title appear here. Okay, so that's the title of the plot. So we have added one more level of complexity here by including a title. Let's move on to the next curve. So you have to now.
Sir, can you move upward for a second?
Yeah.
Okay, sir. Thank you.
Yeah. So now we have to plot a parabola, right? So slightly more complex than a linear curve. So I think you all know what to do now. So I'll just write it down. Now, one thing that I didn't mention, okay, I mentioned that. So number of points, right? If you want 5 equally spaced points, then you have to type in comma 5, right? So that's what you have to do. So y is x square, plt dot plot x comma y, and for good measure, I'll add the scatter also. Okay, and I'll also add a title, right? So it's all straightforward, right? Once you understood the basics, this is just x square. Just use a small trick here to introduce some LaTeX. Not necessary that you should know this. If you add this $, if you enclose the equation within a dollar, you will get it like the normal math expression, right? So if you don't use the $, then it'll appear a little bit weird. Okay, so it'll explicitly whatever you type it'll appear. But if you use this $, then basically it's using LaTeX, right? For those of you who know LaTeX. So just enclose your equation within $2.
Okay. So can you just repeat once more why we should use $?
So $, it comes from this it's the syntax that you use to in typeset math equations, right? So for typesetting, if you want to typeset math expressions, you use this tool called LaTeX, right? So typically in many places, if you want to enclose a mathematical expression, if you want to type it out the way we actually write math expressions, you enclose them within $2. Okay, if you don't use these $, it will appear as with the caret symbol, it will appear, right? And that's also quite clear. But then if you want, if you are someone who cares about aesthetics, then you will add this, right? So, but the more important or interesting thing is this, right? So is this a parabola?
No, sir. It's look like, but not exactly.
Right. So this also gives you an idea of what matplotlib is doing, right? It's actually, if you just recall, it's just connecting 2 points by straight lines, right? It's connecting 2 points by straight lines. That's all it does. So now let's go back to the question, right? The question is asking us to do 5 equally spaced points. That's what we did. And then it's also asking us to do 10 equally spaced points. So let's go to 10 points. See, currently there are 5 points, right? 1, 2, 3, 4, 5. Let's run it with 10 points. Okay, it's slightly smoother, right? At least it's smoother than the previous one. If you use 20 points, it look even better. Okay, and if you use 50 points, you basically can't tell what's happening, right? Now we can remove the scatter because that's a bit misleading. Okay, right? So that's, you can't really make out if it's actually what has happened, it has drawn 50 straight lines. Okay, so do you all see that? Matplotlib has internally drawn 50 straight lines. Okay.
So if the number of sampling is more, then the curve will be in a better manner.
Exactly. Yeah. The more smooth it will appear to us, and if you have enough number of data points, you'll basically not be able to differentiate between like whether it has been done using straight lines or whether it is actually a parabola that has been drawn, right? So okay, so
so for this, this seems we all know like y equal to x square should give only a parabola. So it's mandatory for us to use a high sample. There is no other way, no, sir, to get this plot to look like a parabola to match that equation y equal to x square. We ought to go for a higher sample. There is no. It's mandatory to put a 50 plus 50 or something. We can't just do with 1 or 2. Then Matplotlib will not represent that equation at all.
So see, the appearance will clearly not be that of a parabola, right? So,
but we all know like it's that equation is for a parabola. So the we ought to mention a high number there as a sample for the Matplotlib to match that equation.
That is true, right?
It's mandatory, I believe.
Yeah. By default, link space accepts 50 points, right? So if you look at how many points it accepts, the default value of the number of split points is 50, right? So it is already high. So in some sense, it will be taken care of. But you are right. So if you want something like x square, so we should go for a high number of split points, right? So that is y equal to x square, and now.
So a quick doubt. So in this, how we have used the arrow for superscript. How can we use it for subscript? That's in L2 norm. We can represent 2 in the subscript. So how can we use it?
You just use an underscore, right? So just use an underscore and you'll get it, right? So
underscore. Okay.
Yeah. Okay. So we'll move on. So the next curve is. Yeah. I mean, yeah. I'm sorry. Like we'll more and then we'll get back to the question, right? Only 2 more. So I'll finish this and you can ask me. Okay. So we have to plot simple lines now, right? Y equal to 3, x equal to 5 on the same plot, and we need to give them different colors. Okay, so this is what we have to do, and limit your plot to the region x equal to x belonging to 0, 6, y belonging to 0, 6. Okay, let's go step by step. Let's first plot y equal to 3. Okay, we are first going to plot. Forget about the color for now. Forget about the legend and all these other things. First thing we'll do is plot y.
Sorry, sir. For 1 second, can you go up, sir, in that last plot? There was also, if you can just go up for the instructions, just a little more. It says also add x and y axis to the plot, it said.
Okay, yeah, let's add it now. Yeah, so let's do that now. So x, so the way to add an x axis and y axis is again, there are many other ways of doing it, but one way is ax h line, axis horizontal line. Okay, plt dot axis v line. So okay, so that's how you add this, but it's in the same color as the curve. So let's make it black so that we can differentiate between the axis and the curve, right? So this is how you do it, right? So you have ax h line, ax v line, so horizontal line and vertical line, and you color them black so that you get the axis.
Hello, sir.
Yeah.
Do we need to add the grid lines to understand where exactly the points lie on that parabola? The grid line?
That is also a good point. So we can. So if you have this then that will help, right? So that's a good point. We can add the grid also if you want.
So it's easy to understand where the point lies actually. Okay,
Right.
sir. Thank
Yeah.
you, sir.
Is it
sir.
sorry, in this case, American English is applicable because what you mentioned, color spelling.
Okay, so let me finish this and I'll get back to that, right?
Sir, how you did the grid lines?
Okay, so it's just plt.grid of true, right? I'll get back to this, right? So I'll get back to some 1 or 2 questions. I'll just finish curve 4 and subplots, right? So we want to plot y equal to 3. So y equal to 3 will be what? Horizontal line or vertical line? What will it be? Will it be?
It will be a
Horizontal
line.
Horizontal line.
Okay, it's horizontal line, right? So let's look at x, right? You want the interval, that's where you are going to plot 0 to 6. So np dot linspace of 0, 6, by default 50 points will be taken. So I'm not mentioning how many points. So corresponding to this, if I want to plot y equal to 3, what should be my y values?
Only 3.
Okay, I'll take that as an answer and let's see what happens. Okay, let's run this. It gives us an error. Let's see what the error is. It says x and y must have the same dimension, but x has a dimension of 50 because you took 50 points, and y has only 1 point. So y has dimension 1, or rather, y is a scalar, right? So
basically, y should be
Then maybe
dependent on
np dot 1
np dot ones of 50
into
multiplied
scale
by
3.
3.
correct, right? So np dot 1s of 50 and you scale by 3, right? Now let's plot. Okay, so that's what you get. You get it at 3. Of course, the graph is not, the origin is not to be found. We'll fix that later. For now, this is how you do it, right?
One quick question, sir. One quick question. How do we know it's 50 points in X? Is that a default?
Yeah, that's a default. So the safe way is to compute that. So x dot shape, right? X dot shape here will be something, right? So you take the 0th element of that. So, and then you set that as n, and then you create as many ones as there are elements in the previous array. So that's a safer way of doing the same thing.
We could also do y equal to np dot linspace 3, 3.
That's a good point. You could do that. So that will basically create 50 copies of 3, right?
Yes.
Yeah. So right, I think that should also work, but this is one way of doing it, right? So getting a list of ones and multiplying it by 3. Okay, so we are done with one plot. We have to color this green, right? The first one is green. So coloring a plot, as you already saw, it's not very hard. So that's all you need to do. Okay, add a color. So it's green. Now let's plot x equal to 5. So what should be x here and what should be y?
X should be np
That
dot
should be
1s
Okay, x should be np dot 1s
of n into 5.
Okay.
Y should be np dot linspace 0 to 6.
That's good. Right. So that's what we need to do. So now let's plot x comma y. We color it red. Okay. So you have the curve that you're looking for, right? So we are done. So we are done with plotting these two. Let's now go ahead and add the axis. Just plt.ax horizontal line, color equal to black, and plt.axis vertical line, color equal to black. Okay, so that will add the axis. Okay, now we are not done. We have been asked to add a title. So let's just add a title. X equal to 3 and y equal to 5. Other x equal to 5, y equal to 3, right?
Sir, can you explain the line number 4 once again?
So 4, you're creating 50 ones, right? So you're creating an array of ones of size 50. and then you are multiplying each of the elements by 3.
NP dot ones in what does it mean?
We just saw that, right? It will create a vector of ones. So np dot ones of 5, for example, will create a vector of 5 ones. And then if you multiply it by 3, you will end up with all 3s.
So NP dot plot is a two-dimensional plot, is it?
Yeah, this is all 2-dimensional.
Okay, thank you.
Okay, so this is x equal to 5, y equal to 3. We are done with the title. Now we have to add a legend. Okay, so legend for to add a legend. Yeah.
I have one more question. We are giving the same variables as x and y for both the plots. Is that not going to overwrite one over the other, or it doesn't really matter? Once it draws, it forgets about that.
Right, the variables will be overridden, but then as far as the plotting is concerned, you have already plotted. So that is recorded, right? So it doesn't matter if you now change x and y.
And it appends to the same plot.
It appends to the same plot, yes. Yeah. Okay, so yeah, what we have to now do is legend, right? So we have to add a label. So if you want to add a legend, meaning which curve corresponds to which color corresponds to which curve and all those things, you have to add a label, right? Only then you'll be able to create a legend out of it. So label here is what we are plotting y equal to 3, right? So that will be the label. Of course, you can change this, doesn't matter. And you can also likewise label this one as x equal to 5. Okay, now adding a label alone is not enough. If you want to add a legend, then you have to call this legend function. Okay, so notice what has happened. A legend has appeared here. So it is mapping the green color curve to y equal to 3 because that is what your label said. Okay, so map y equal to 3 to the green color, x equal to 5 to the red color.
Sir, why the semicolon is used after legend?
Why?
The semicolon after the legend, why it is used?
That I mentioned, right? You want to suppress. I want to suppress this output. I don't want this output. So
if I want to change the position of the legend from right hand side to left hand side.
yeah, we can actually. So let's just look at what. So there's a way of positioning the legend. So let's see what is the. Okay, there's a handles, there's a labels, there's a location parameter. So let's say lower right. Okay, it says that there is a location parameter. Let's try that. Location. I don't know if this will work, but we can try all. See. So you can play around with this parameter called LOC. Okay, so what I just did was using the collab to give me the documentation associated with the command. So for example, if you type in the command and then you enter a question mark right after it, right? So you want to know more about what legend is, right? And if you run the cell, it will give you the entire documentation associated with that particular method. So for example, it will give you what are the variables, parameters passed, what is the return value, what all it will return. Okay, so for example, here it returns something called a matplotlib.legend.legend object. Okay, so all these things it will give you. So there's a way of using collab to get help on what a particular function is doing. Okay, so that is with respect to all these things, right? So now I'll just quickly go over the subplots.
Sir, can you scroll up for a second?
Yeah. So this will be available if you want to.
Thank you, sir. Like that.
Yeah. So subplots, right? So what is subplot? Subplot is okay, this is just basic plotting. So subplot is, as the word suggests, right? You want to have multiple plots in the same figure, right? You want multiple plots in the same figure. So in this case, I want to plot 4 curves Okay, not in the same graph, but in 4 different graphs, right? In 4 different windows, but they should all appear on that same figure, right? So that's the idea. So you divide this into 4 pieces. 2, 2 indicates the number of rows, number of columns. The third parameter indicates which plot you are looking at. So 1 will indicate the left top, 2 is right top, 3 is left bottom, and 4 is right bottom. Okay, so let's go ahead and plot these 4. So here x is in the range 1 divided by e square comma e cube, right? So that's the range, and let it be 50. Okay, I'm not changing the number of split points, and you are plotting ln x, right? Np dot log of x. So if you just type plt dot plot of x comma y, that will just give you the ln of x graph, right? And this is not what we want. We want this to be the first among 4 plots, 4 subplots, right? So I just add this term, divide it into 2, 2 grid, and in the first location, plot this particular curve. Okay, so that's what has happened. You will, once I finish the whole thing, you will see what is happening. So let's title this as what is this? This is y equal to ln x, right? So is that correct? So this is y equal to ln x. Okay, so that is what this particular graph is. Now I'll copy the whole thing. I'll also add comments so that we understand what's happening. We are plotting ln x. Next we are plotting e power x. So we are plotting e power x from the range 0 to 3. So this becomes 0. This becomes 3. And we are plotting np dot e. Right? So np dot log, likewise you have np dot e. In fact, we have an np dot x, right? So I'll just introduce that. So what is np dot x? So np dot x, if you notice, calculate the exponential of all elements in the input array. That's what it does. Okay, so np dot x exp. So let's do np dot exp of x. That will be y, and we call this e power x. Okay, so this should be 2 comma. So see, because I didn't change this index, it plotted it on the same subplot. So we have to change this to 2 comma 2 comma 2. Okay, so that gives you ln x on one subplot, e power x on the third subplot, right? So we have done 2 curves. Now let's go ahead and plot sin x from 0 to 2 pi. So this is sin x from, this is the third subplot, and it goes from 0 to 2 into np dot pi, and we are plotting np dot sin of x. Okay, so this is sin x, and you end up with something like this. So there is some overlap here. We'll correct it soon. Finally, we have to plot y equal to 1 by x from 0 to 5. Okay, so this is the 4th subplot, and you plot 1 by x. Okay, now we'll end up with some problem. And can someone tell me what problem we will end up with?
1 by x leads to infinity.
Correct, right? So this division by 0 is a problem. Okay, it's giving us a warning. So it's not saying that it's wrong, but then division by 0 is a problem, right? So what we'll do to fix that is we'll just start from 0.1 instead of 0. Okay, so that we don't get this 1 by 0 problem. Okay, so we have just started from 0.1 instead of 0. Okay, so that's what we have. Now there is some overlap, and it's slightly cluttered. So what I'll do is there's a way to fix this by making the entire plotting window bigger. So so you can for now memorize this. We'll come back to this later. I'm going to make the entire plot slightly bigger. Okay, and this is the command to fix or rather alter the size of the figure itself. Okay, so in fact, I think I made it smaller. So let me make it 8 by 8. Okay, so that's much better, right? So figure dot fix size. So this RC params, if you notice, it's actually a dictionary, right? It's a Python dictionary. One of the keys of this Python dictionary is figure dot figure size. And if you change it, it actually accepts a list of two values. Okay, and if you give a size like 8,8, that will give you a nice space to plot the 4 subplots.
So the sin x, so can you go to the sin x part of the code? It's linspace 0 to, okay, NumPy, NumPy, okay. And
Sir, can you go up that figure dot figure?
Okay, so that's what we have for plotting, right? So this is like basic plotting for.
So can you just stay on the code, sir, for 2 minutes?
Yeah. Okay. I have a feeling that we may not be able to finish all 5 collabs today. So let's see how many we can. Okay, so shall I move on? See, this whole thing is available here. It will remain.
So why is there a slash before the ln and the sign?
Okay, so that's again that has to do with LaTeX, right? So, for example, the LaTeX syntax for natural logarithm is /ln. So, I mean that's not very important, right? So you can ignore that part.
Okay.
Okay, so I'll move on now to.
So last, just the code, last bit.
Yeah, so if you are.
Got it.
Yeah. Okay, so I'll just close this and move to matrices, and let's see how much of it we can do today.
Sir, are you speaking?
Yeah, no, it wasn't. Yeah, let's start. So let's import NumPy NP. Right. So everything in NumPy is an array, right? So you saw that vectors were arrays. Now let's go ahead and see what a matrix is. Matrix is also an array. And this is how we create a matrix, right? So it's a nested. If you were to do it in Python, what will we do? We'll do a nested list, right? So this is how a matrix in Python will look like. Correct? Nested list.
Yes,
Okay, so what we do in NumPy is again just whatever we did for vectors, right? We just enclose the whole thing within an array, right? We make it a NumPy array. So you don't need to do this spacing thing, but just so that it's more readable, I've done this. So you have now created a matrix in NumPy. Okay, it's a nested list in Python, and this is a NumPy array in NumPy.
Interruption.
Yeah.
Interruption. I can keep them in the same line also. That's okay.
Yeah, we can do that. Yeah.
Okay.
Sir, instead of doing it like this, can we do it like split it across 3 cross 3? Having a single list.
You mean create a list of 9 numbers and then.
Yeah, split it across 3 cross 3. Is it possible?
Yeah, it is possible. Yeah, we'll actually come to that very soon. So we can do it.
Thanks, sir.
So this is a matrix. Now, see, all these things are very similar, right? So whatever we saw earlier, so that's what is going to happen, right? I'm going to create 3 matrices. So that is A, nested list of So that's what we did. So A is this. Now this is 5, 6, 7, 8. Right now, how do you add two matrices? A plus B. That's all. Right. So you just do it. You get 6, 8, 10, 12. Right. Nothing different from vector addition. Matrix addition is element wise, and you're just adding two NumPy arrays. Okay, no difference here. Scaling a matrix is also works in a similar way. Let me just copy this. We are calling it M. So it's 1, 2, 3, 4, 5, 6, 6, and 7, 8, 9. Right. So if you do 3 times M, you just need to do this. Right. So you get element wise multiplication of a matrix by a scalar. Okay, nothing changes here. In fact, element wise multiplication of matrices is also very simple. I'll copy this. Okay, because it's the same thing. You have A, you have B, you want C equal to A into B. Again, if you simply use the star, you get element wise multiplication. Okay, nothing different from vectors that you saw before. All of it carries over. Now, again, like in vectors, we had element wise application of some function. We can do the same thing here. So assume that you have this matrix A as -1, 2, -3, -4. Right? You want the absolute values of each element in the matrix. So you can do this np.apps of A. Right? np.apps will just give you the absolute value of each element. Okay, so for example, np.apps of -5 will give you 5. Okay, so it's simple. That's how element-wise operations happen. Now, this is just.
Sir, can you go again? The previous one.
Yeah. So if you're writing these things down, please. It's not necessary, right? The collapse will be available for you, right? So don't worry about writing it down. It's all available. So, okay. So I'll again do this part very quickly. So you have 1 √2. So how do you write √2 in NumPy? You can either do 2 power 0.5. That's how you do it in Python. In NumPy, if you want, you can do np dot.
SQRT.
Yes, that's correct. Right? np dot sqrt of 2 and np dot sqrt of 3. Okay, so that is what A looks like. So 1.414 and 1.732. Okay, now we want to do B is equal to A square. Okay, not A into A in the matrix multiplication sense, but element wise. Okay, so if you do B equal to A star star 2, you will end up with 1, 2, 3, 4. Okay, so these are all very simple, right? Whatever we did for vectors, same thing happens for matrices. Okay, so now we start looking at slightly more interesting things. So here we want the transpose of a matrix. So you all know, very important operation in linear algebra. So how do we do this? There are again 2 ways to do this. One is to do np dot transpose. Okay, so np dot transpose of M. Okay, this is one way of doing it. But then NumPy has a very simple.
Please comment that, not erase.
Okay, yeah, makes sense. I'll do that. So thankfully, NumPy gives you another way to do it. Okay. Again, similar to the dot product that you saw, where we used A at B, I would strongly urge you to use M dot T instead of NP dot transpose, because the translation from math to Python is neat if you use M dot T. Okay, so that's one point. Okay, now we come to the whole idea of dimension, and I hope this dimension business will be a little more clear now. So it's the same matrix, right? So I'll just copy this. Okay, so you have a matrix here, right? So what do you think M dot shape will be? What do you think?
2,3.
2,3, right? So 2,3. Right? So this is the exact idea of shape or dimension of a matrix, or rather, I should not use the word dimension. This is the idea of a shape that you are all familiar with, right? Now, what do you think will be this whole idea of NumPy dimension?
1.
Two.
Okay, so this is what.
Talk about axes.
Yeah, right. So this is what we mean by dimension, right? So there's actually one vertical dimension and one horizontal dimension. So matrix is what? A grid of numbers, right? So a grid is basically a two-dimensional object. Okay, so grid is 2D object. The shape of a grid is rows cross columns, right? So the shape is going to give you number of rows into number of columns. So there's no denying that, but the dimension, the NumPy dimension is going to be how many such axes you have, right? Number of axes that you have, right? You have a grid, right? And a grid is 2D, right? And therefore, m dot ndim is going to be 2. Okay, so this idea of a dimension clear now. Vector is one dimensional because there's only one axis along which it moves, whereas a matrix has two axes along which it can move.
And one quick question, sir.
Yeah.
Like here when we are calling some functions, like when we call np dot transpose, within the parentheses we are passing that matrix, right?
Yeah.
Sometimes we are passing the parameter. Here also when we are calling m dot shape, we are not passing any parameters. Is there any thumb rule kind of thing when to pass parameter and when not to pass parameter?
Okay, so
Already just based on experience.
Okay, some functions, some methods accept parameters, right? So I'm also not sure what m dot shape is going to return. Is it? Okay, so this is a property. It says this is a shape. So this is an attribute. This is like it's not a method of.
It's an attribute, right?
It's an attribute, right? So it's not a method of the object.
Okay, it's an attribute.
So if you use a method of m, for example, m of sum, then you will have some parameters associated with it, right? So m dot sum will be a method. So if you just call m dot sum, it'll just say that it's a function. And
let us take the example of transpose. When we call transpose by using np dot transpose, then we pass that matrix, right? But when we use m dot transpose, so how come the same transpose in one place acting as a function and another place acting as an attribute?
No, they're different calls, right? You are calling m dot t here. On the other hand, you're doing np dot. You're calling a method of the NumPy module, and you're passing a parameter into it. Both essentially are doing the same thing. Okay, but one is a function of a module, and the other one is some kind of a property of an object.
Okay, sir.
Okay, so vectors as matrices, right? So we can also, you all are already aware of this. Vectors are what? Typically, we treat them as column vectors, right? So any vector you have, it's a column vector of shape d cross 1. Matrices are of shape 1 cross, row vectors are of shape 1 cross d. So let's take a vector. Let's say 1, 2, 3, right? We all know that x dot shape is going to give you 3. Now we could also treat this as a matrix of dimension 3, 1, right? It's a column matrix. A column vector is actually a matrix of shape 3, 1. Okay, so one way to do this in NumPy is to increase the dimensions, right? NumPy dimensions. So expand dims. What you're asking it to do is expand the shape of an array, as it says, right? Very usefully it suggests. Expand the shape of the array X, okay, along the axis 1. Okay, add one more axis. So if you now print x dot shape, okay, I'll just call this X column matrix, right? And if I print the shape of this object, I get 3, 1. Okay, this may be slightly non-trivial at first sight. So see, the shape of X is 3. Okay, and that's a vector, so there's no problem with that. But then we could also treat it as a matrix of size 3, 1. Okay, and if you want to do that, you have to increase the dimension of the array by 1. And this is how you increase the dimension of an array by 1. Do you all get this part?
So can we increase more
No.
dimensions?
Okay, that's a good point.
Can you repeat this from start, please?
We did not get
So the
that,
first line
sir.
is
Can
clear.
you
The
repeat
second
it
one,
again?
second line was
Okay, so see, there is this array, right? So
right.
What is the shape of x? X is a vector. So x is a vector of shape this, right? So
yeah.
So that is the first part. Now, sometimes you might want to treat this as a matrix, right? So we typically do this, right? So we think of this in mathematics as a 3x1 matrix. Is that right? That's how we have been looking
Yes, sir.
at all the
Yes, sir.
I want to do something similar with NumPy, or at least NumPy should give me the ability to deal with a vector as a matrix. Okay, a NumPy matrix. So how do I do that?
Can I request you to pause here? Can I request you to pause? Right now it is giving it as 3 comma.
Correct.
The 3 represents the 3 elements in there, which
3.
are in the column wise, right? Or are we counting the rows?
No, there is only one dimension, right? So basically there is only a row basically, or a column, right?
Okay.
We only have one axis.
Yeah. So it's
Okay,
the one
fine.
that's right.
Fair
So now we want to expand it, expand the dimension, or we want to add it. We want to add one more dimension. Now the question is, where do you want to add it? You want to make it a row vector or a column vector? So if I add axis equal to 1, it will give me a column vector. So whose shape is 3, 1, right? So now let's x underscore call mat is a matrix of shape x underscore call underscore mat, right? So that's what it's going to give you. So it's going to expand the dimension, or rather add one more dimension, but along the axis 1, which means make it a column vector. Now I could also do it as axis equal to 0, in which case it'll turn it into a row vector. Now let me type it out separately here. Let me call it x row mat, but instead of making it a column vector, make it a row vector. So that's what I'm asking it to do. Okay, so notice that this is now a row vector of shape 1 cross 3. This is a column vector of shape 3 cross 1. The underlying object is the same. It's this 1, 2, 3 only. But sometimes I may want to treat this as a matrix. In that case, I have 2 options. I can either treat it as a row matrix or a column matrix.
Okay.
Sir, can you
the
display
axis be
both of
interpreted as a feature?
The axis, well, if you look at a matrix, you can treat each column as a data point and each row as a feature.
Correct.
Right. So, yeah, you could do that.
So can we instead of 1, can you write 2 axis equals to 2?
Yeah, I'm actually not sure what will happen. So, but I'll try it out as you say. What error does it throw? It is out of bounds for array of dimension 2. That's what it says.
Values are only 0 and 1, sir. 1 for column and 0 for row.
Right. So had your array itself been 2-dimensional to begin with, right? So for example, let's say your array was actually a matrix, right? So let's take this particular matrix. Okay. I'm not sure if this will work out, but let's just try. So if you want to add one more dimension for this matrix M along axis equal to 0, okay, we call it M underscore new. That works, right? So you can add, if you look at the shape of M new, it'll actually be 3-dimensional object where you added one more axis. Okay, why we would do this? When does this make sense? We'll come to that later. Right now, I don't have an answer, but you can.
So could you please print it?
print you want to print M?
Yes, sir.
Okay. So notice that there is, instead of 2 brackets, there is 1 extra bracket here. Okay, so if in fact if I do m nu of 0, you will get the original matrix back. Okay, that's what this new axis actually did for you. Okay, but this is, let's not worry about 3 dimensions now. Okay, let's get back to 3 dimensions a bit later. For now, if you understand how to treat vectors as matrices, that much is enough.
So in line number 3, if you interchange the places within the parentheses, what will happen?
That's
Interchange of those 2 elements. Like first you put accessing X.
Okay, that's a problem. That's not allowed. Python will not allow that, right? Because it will always say that.
No, I was thinking like X comma axis equal to 1. It was literally taking the number of elements. Like X has 3 elements. So 3 comma axis equal to 1 means 3 comma 1. So that's why it's printing 3 comma 1. So that's why I just asked you to interchange. Okay, sir. Now I got it. Some conceptual.
Right. So next we come to the perhaps the most important operation in all of NumPy, which is matrix multiplication, right? So the interesting thing is there are like several ways of multiplying matrices. Once you introduce the idea of a vector also being a matrix, right? So you can multiply 2 matrices, or you can multiply a matrix and a vector, or you can multiply a vector and a matrix, or you could multiply 2 vectors. And even in vector multiplication, you could do it multiple ways, right? So very quickly we look at what each of these is. Okay, so this is a 2 cross 3 matrix. So 1, 2, 3, 4, 5, 6, and you have B, which is 6, 7, 8, 9, and 10, 11. So we have, let's print the shapes so that we know what we're talking about. Print A dot shape and print B dot shape. Okay, so we have a 2 cross 3 matrix and a 3 cross 2 matrix. They are compatible for multiplication. Now you want to find out A into B, which is simply this. Okay, so again, the at symbol comes in handy here. Recall that we use this for the dot product. For the product of 2 matrices, you just need to use the same thing. Okay, notice that this is not the same as A star B. A star B is element wise multiplication. It will throw you an error because they are not of the same shape, right? Only if they are of the same shape can you multiply them element wise, right? So star is element wise, at is matrix multiplication. Okay, remember that. Now that is matrix. Now you have a matrix vector. Okay, so let's see how we do this. Okay, I'll just 4, 5, 6, and 7, 8, 9. And you have np dot array of 6, 7, 8, right? So you want to do A times X. Interestingly, the same command works for matrix vector also. Okay, so the reason it works is internally what NumPy is doing is it is going to expand the dimension of X so that X becomes a column vector. Okay, so let me just print the shape so that it is clear to all of you. So notice that A dot shape is what? 3 cross 3. And ideally, when can you multiply a matrix and a vector? Only if this vector is 3 cross 1, right? Only then I'll get, I mean, it makes sense, right? So what NumPy is doing is internally it's doing that. It will make this vector 3 cross 1 column vector so that it becomes compatible for matrix multiplication. Okay, so is this part clear to all of you? What happens here? Any
Basically,
questions?
sir,
Yes, sir.
we do not need to explain dimension here.
Right. Okay. So internally that's taken care of, right? So that's the main point. So this is matrix.
X at A. Can we do X at A?
We'll come to that, right? That's the next step, right? So that is vector matrix, right? Row vector matrix multiplication. So if you want to multiply X transpose A, you can't multiply X into A, right? Because they are not compatible for multiplication. However, you can try X transpose A. Okay, so we'll do that. Okay, so I want X transpose A, and it turns out the code is the same for that also. You just need to use that. Can someone tell me what NumPy will do internally here?
It will transpose, right? That's
Change the dimension of x to 1, 3 from
And the dimension.
Exactly, right? So it will expand the dimension of X to 1, it will expand it by 1, but in such a way that it makes it a row vector. Okay, so X will now become internally a row vector so that matrix multiplication can happen between X and A. So this is what row vector matrix multiplication is, right? So X at A at X, and then A at B. It's the same syntax, but then you can use different operands on either side. Okay.
Does it mean that we don't need to transpose this row vectors?
No, right? So that is done internally. In fact, this is a good place to introduce this. The transpose of X is actually X itself, when X is a vector, right? So if you do X transpose, you will see that nothing happens, right? It's the same thing because there's just one dimension. Okay, right? So, however, if X had been, expand dimes of X comma row equal to, axis equal to 0. So if you had made this let's say a row vector, right? So X dot shape is 1, 3. Now if I do X dot T, okay, and then ask what that shape is, then it will be 3, 1, right? So that transpose still works because you have explicitly expanded the dimensions so that it becomes a row vector and then done the transpose. So there you will get different results. But if you just do it on a single dimensional array, X dot T will be the same as X. Okay, so that's one part. The next, we have already seen this, right? Dot product. So inner product. So X transpose Y is nothing but dot product. And you all know that that's actually an inner product between two vectors. It's actually, you can look at it as a product of a row vector and a column vector. Okay, so it's the same as np dot dot. Okay, so, and as you can recall, we did x at y there. Okay, so for dot product also you have the same syntax, or for the inner product it's the same syntax, right? Finally, we have what is called the outer product. So can someone tell me where we saw the outer product in the MLT course or MLF for that matter?
Projection
Covariance
matrix.
matrix. Covariance matrix.
Right, so we were saw that in the covariance matrix it was sigma xi transpose by n, right? So there we use the outer product. So let's try this, okay, and see what happens. So y equal to np dot array of, okay, so will this work? Will this give me the outer product?
No, sir.
No, it will give me only the inner product. So what should I do if I want the outer product?
We need to expand the dimension, I think.
Correct, right? We need to expand the dimensions, right? So again, those who say transpose, notice that y dot transpose is just y. It's a single dimensional array, so it will not work. So you have to expand the dimension. So let me call this x new. So expand the dimensions of x. So you want to make it a row vector, right? So no, column vector. So x is a column vector. So what should be the axis?
1.
1, right? So I make it a column vector. Y new is, I make it a row vector. So the axis is 0. Now if you do x new at y new, okay, you will end up with whatever you're looking for. It's a matrix, the outer product of these two vectors. Okay, and that's exactly what you want. Okay, so these are 4 different ways of multiplying matrices. Okay, and you must be aware of all of them. Okay, so that is one stage. Now it's already 10. So those of you who want to drop off can drop off. I want to at least finish this collab. Okay, so those who are want to drop off, I think you can feel free to drop off. The attendance will
How
be
much is left?
it's like we have quite a lot left. I'll maybe do till 11 and then I'll stop. But it will anyway be recorded. So
Where do we get the video, Karthik? YouTube? How can we access?
I think we'll upload it. I don't know when, but I am sure we'll upload it.
No, where? Do we get an email or in the course?
No, you can look at the.
Sir, can you get back to that cell, like the last cell, the outer product?
1 second, let Karthik finish. Where do we get the
We have
YouTube link?
our channel, right? BS degree channel. So
Okay.
that if you go to the videos section, we'll upload it. Or if worst case, we'll mail all of the participants the link. Or one thing I'll do, this is easier. So I will create a sheet here and add a link.
Okay, yeah.
That will be wonderful, and put the PDF also there only, sir.
Yeah, I'll do that.
Thank you.
Right, so I'll continue and finish this off. So what happens if you want a matrix of zeros? Now recall that if you wanted a vector of zeros, we did np dot zeros of 5 or 6, whatever. Now you want a 2 cross 4 matrix of zeros, right? So this is all you have to do. Okay, so that's matrix of zeros. If you want a matrix of ones, then np dot ones of 3, 2. So you have to enclose it in. So you actually should have a tuple, right? So you should have a tuple here. I'll show you what happens if you don't have a tuple. So if you don't put it in a tuple, then it will complain, right? So cannot interpret 2 as a data type. It's actually expecting a tuple. So you have to enclose this in brackets. All right, so that's how you do this. Now, nothing new there. Identity matrix is interesting. It's a nice command. np.i of size of the matrix, right? So
question. The earlier one is regular brackets, not square brackets, is it? The ones and the zeros.
Right, it's a tuple, right? So tuple should have.
Okay.
So let's try. I think this will also work, though I'm not exactly sure. It works, right? So it doesn't matter.
Okay. Okay.
Okay. So identity matrix is I, right? I stands for the I, right? So for whatever reason, this is the one which they went for, the developers. So np.i of 3, just give the index of the identity matrix. We'll get the diagonal matrix is also quite simple. np.diag of 1, 2, 3, 4, right? Whatever is your diagonal elements, just put that in a list, call np.diag, it will give you the diagonal matrix. Okay, so that's the few special matrices. Now, the most important part is slicing, right? How do you index and slice a matrix? You're all familiar with indexing and slicing in vector, in lists, right? So, for example, if you have a list like this, so 1, 2, 3, 4, 5, and you want to just bring out 2, 3, 4. Okay, what do? You take L of
1 slice column
till where would you go?
plus 1. 1, 4.
Okay, so if you do this, then you will end up with 2, 3, 4, right? This is usual list slicing. Very similar thing happens in matrices in NumPy, right? So first, let me.
First element is not identified as 0 in this case. And like normally the list actually starts as 0, 1, 2, 3, 4 as the
correct. Yeah, position. We do 0 indexing. I wanted the second element onwards. That's why I had done
but
that.
When you said 2 on 1 and 4, it did not take the 4. Okay, sorry, my mistake. Yeah, got it. I made a mistake.
Right, so this is M. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So we want to extract the third row of M, right? So remember that M is also a nested list at the end of the day, right? So you can just index the first element. Think of the first index as the row index, right? So M of 2 is going to give you the third row, right? So M of 0 will give you the first row, right? So it's just a nested list. You can treat it as a nested list and get hold of the rows. Okay, this is one way of doing it. The other way I'll come to it. Well, maybe we'll do column slice. It will become clear. Okay, so what is the column slice here? Let's. Okay, so this is M. So M is 3 cross 3 and looks like this. You want to extract the second column from M. So what is the second column? Basically, you want all the elements, all the row values, but you want to fix a particular column value, right? So the way I denote this is, give me the entire row, give me all the rows, but then fix the column as 1. Okay, so this may be slightly new if you have not seen this before. The column is essentially telling you, just give me all the elements along that axis. Okay, you can treat this as two axes, right? The top to bottom axis, the left to right axis, or the axis that governs the rows and the axis that governs the columns. So you fix the column to 1 because I want the second column, right? So I fix the column index to 1. I don't fix the row index to anything because I want all the values that are there in that particular column. So I say M colon comma 1. Do you all get this particular idea of column slice?
Yes, sir.
Okay.
Yeah.
You could go back and do the same thing for a row. Okay. So the row, I want the second row. So I fix the row. I want the third row. So I fix the value of the row index to 2. But then I want everything from all the values in the columns corresponding to that row. Okay. I'll get the same thing. But it's better to be consistent. So we use this. Okay. So that is row slice, column slice. Now let's say we want a sub matrix slice. Okay, so I am not going to type the whole thing. There's a shortcut. We'll come to that shortcut maybe tomorrow or whenever. So I'll just create all the 16 values. I shape it like this. Okay, we'll see reshape very soon. Okay, so you don't need to worry. So I just want to do it quickly. So I did it this way. So this is 1 to 16, right? So this is the matrix M. I want to slice from the second row to the third row. Okay, so I just give enough space here so it's clear. So I start from the first row, meaning that
column 4.
Okay, till what?
4.
Okay, is it 4?
Yes,
No,
sir.
3, isn't it?
Yeah, 3, 3, 0, 1.
So this is 1 to 3. What about the column?
Same.
2, 4.
Okay, so this is 2, 0, 1, 2, 3, 4, right? You need 4. So the space doesn't matter. I'm just
Sorry, 1 second. There are only 4 columns and it is 0 indexing. So when we say 4, it actually goes to the 5th column, doesn't it? Or am I mistaken there?
So if you add 3, right, 3 will not be included, no? So 0, 1, 2, 0, 1, 2, 3, it will just stop with the second column, right? The last index is not included. So you can either add 4 here or you can just leave it blank. I'll just print this out and we'll see. Okay, so this is what we get, right? So I can either add 4. In fact, I can add any number here, it doesn't matter. But better to leave it empty. Okay, or
Sir, can you explain this one more time?
see, I want.
But just correct me if I'm wrong. The columns are also 0, 1, 2, 3 indexing. Wise.
Correct. 0, 1, 2, 3. Now let me add 3. What do you think will happen?
Only 7 and 8.
It will only
7 and
take one
11.
column.
Okay.
7 and 8, because the second column is included, the third column onwards is excluded. I mean, the third column is excluded, right? So third in the sense the fourth column. Right? So this you should not include this index 3. So start from 2 and take everything until 3 minus 1.
Yeah.
Right. So now therefore you have to add 4. Since 4 happens to be the last, I mean the end of the array, you can also leave it. It will not matter.
Okay.
Okay, so that's how you get a submatrix slice. Okay, is everyone clear with slicing and indexing? This is like bread and butter because of ML, at least the data engineering part, right? Because if you have a data matrix of size d cross n, sometimes you may want to pick the 7th data point, right? So how will you pick the 7th data point? If X is your matrix and you want to pick the 7th data point, it will be
2,3.
Right? So it will be 6. So what will this column be? It will be of dimension d. It will be of dimension d. It will have the d features corresponding to your 7th data point. Okay, so this is like, that's why it is important. So slicing and indexing is important for one of the reasons is this, right? It's not the only reason. So, okay, so that is slicing and indexing. Now, okay, there are like a bunch of things that you can do once you have a matrix in place.
I didn't get what you said regarding the 6th data.
So for example, assume that this is your data matrix, right? So there are 4 features and 4 data points. Okay, so it's like a 4 cross 4 matrix. So each column will be a data, it's like a feature vector, right? A data point. So let's say I want to extract the 3rd data point and look at its features, right? So what will I do? I'll do colon comma 2, right? That will give me 3, 7, 11, 15. That is what I was talking about. Okay, so I'm not going to do this in all the detail because we may not have that much time. So I'll just take hold of this matrix and demonstrate only the inverse part of it, right? So let's say this is the matrix, right? So you want to find the inverse of this matrix. First of all, this is a square matrix, right? So you can talk about the inverse, okay? But then inverse need not exist, right? In fact, here will the inverse exist or not for this particular matrix?
No, it won't.
It won't, right? So one way to figure that out is to find out what the rank of the matrix is, right? So you do np dot lineage dot matrix underscore rank of m. That will give you the rank of m. In this case, the rank of the matrix is 2, right? It's not a full rank matrix. So the inverse is not defined. So if you still persist in going and finding the inverse, then it will throw an error, right? It will throw a linear algebra error. Says the matrix is singular, right? So singular matrices, you can't find the inverse. So in such cases, what have we learned in our course? You have to compute what is called a pseudo inverse, right? So thankfully, the pseudo inverse exists for every matrix that you can think of.
What's the command for inverse? I just missed that.
The command for inverse is just in.
Yeah, got it.
Okay, so the pseudo inverse is simply P inverse, right? So it's not this M, it's the M that I define here. It will exist, right? So it's P in. So that's the pseudo inverse. Now that will always exist. So that's one nice thing. Okay, so the other thing that we use very often is the eigenvalues and eigenvectors. At least in week 1 and 2, we have used them. So I have to write down the matrix, no other go. So let's say this is 1, 0, minus 3, 0, 5, 2, minus 3, 2, 8. Okay, now again, there are several routines out of which np.lineage dot HH. I'm going to HH. It's not necessary that you should go to HH, but eigen H is like Just write it down. It will give you the eigenvalues and eigenvectors of a complex Hermitian or a real symmetric matrix. Since in the PCA case, we usually go for the symmetric matrix. We have a real symmetric matrix, the covariance matrix. Therefore, I'm using this np.linearity.hh. Okay, so that will return two things. If you call it on a matrix, it will give you the eigenvalues and it will give you the eigenvectors. Okay, very clean, right? So you don't need to break your head, it will give you all of this. In this case, it's a 3 by 3 matrix, right? It will give you 3 eigenvalues and it will order them in the ascending order. Okay, so in the PCA sense, if you want to find the variance along the first principal component, what you'll do is you'll go and look for the last eigenvalue in the array that is returned to you. Okay, so that's what you will do. Now, eigenvectors, if you notice, it will be a 3 cross 3 matrix where each column is an eigenvector. Okay, so let me repeat that each column is an eigenvector. So the last column, the first column, will be the eigenvector corresponding to the first eigenvalue. This is the first column, right? So in fact, you can even verify this. So look at, just focus on this. This is the first eigenvector. Okay, so if I multiply m with this eigenvector, what do you think will happen?
Should get the corresponding eigenvalue times the eigenvector.
Correct, right? So let's make sure that that actually happens, right? So I'll do all of these in separate cells so that it becomes clear. So this is eigenvector. Now I'm doing matrix times the eigenvector. Okay, so that should give me ideally lambda times the same eigenvector, right? So let me, in another cell, let me compute the first eigenvalue times the first eigenvector. These two cells should be same. Okay, so do you notice that m times x equal to lambda times x? They are the same. Okay, so what we have actually done is it's a very simple way to compute the eigenvalues and eigenvectors of a symmetric, real symmetric matrix. That's what we have done here. And of course, for those of you who did MLF, MLT together, you would have spent a lot of time on the SVD of matrix. So all you need to compute the SVD. Sorry, this is small SVD. Okay, so it will return 3 values. So it will give you U, that's the first array. It will give you the singular values, that's your second array, and then it will give you the V transpose, that's your third array. Okay, so I've just listed down a very small subset of operations that you do with matrices in this collab.
Sir, sir?
Yeah.
Can you go back to the SVD form? Actually, I have a question. So does this return the singular values that we've been discussed in the MLF, or is it the eigenvalues that has been provided here actually?
I think they are the singular values, but let me check. So linearity.svd. So it's going to return, it returns the singular values, right? So
yeah,
it does return the singular values in this case.
Yeah, sure. Thanks, sir. Actually, yeah, thanks for the clarification.
Yeah. Okay, so here is where we stand. I actually want to discuss collapse 4 and 5. Obviously, we can't do it now. So when do we do this?
Sir, also we are getting it and we will look at it later, but you're for a change, you're really rushing through.
Yeah, because see, tomorrow so I'll come back on Saturday. So before that, I actually thought of finishing all these today. So given that we have only 2 hours for every day, I am finding it difficult to cover all of this. In fact, I wanted to cover 2 more collabs also. Turns out.
Does it mean that you are not taking the class tomorrow?
So 3 of us will be doing it. So we have divided the topics amongst ourselves. So
okay.
The problem is we want to cover all these topics. Given that we have only 4 days, that's the problem.
Can't we go through one more like visualization part? I think it will be easy.
I don't mind. I can go till 11. If some of you are willing to stay, I can go till 11.
Is it okay if we do it Saturday?
Saturday we can do. Okay, we can.
Are these going to be used the next days? I mean, I don't know which way it is that you have constructed the entire workshop.
Okay, so the bar plots, we may not be needing the bar plots, but we will be needing some of these scatter plots. So, okay, let me go. So, we won't be needing NumPy array, more on NumPy arrays. That I think we can skip. We can move that
for
to
now, but yeah.
Okay, let me see what all we have in NumPy arrays. We need to. So I need to talk about reshaping and that can wait. Advanced indexing, these can wait, but okay. So I prefer doing one more now. Okay, and the last one I'll do it on Saturday. Okay, so if anyone wants to drop off, please do so. It's not binding on you to stay. It'll anyway be available, right? Recording. So
It's not so much dropping off. It's not about the time. We can stay, but it's become a little overwhelming. But I guess we'll go back and watch the video. You go ahead, sir.
Yeah. So I understand that it's like too fast, but maybe we should have reduced the number of things we wanted to cover. But yeah, let's try our best
Fine,
to.
sir. We can watch it again. It's fine.
Yeah. So.
Can somebody put the link of this again, the collab, in the chat somewhere?
Sir, when is the exam actually planned so that we'll get enough time to go through this and get in everything, sir? What is the expected?
It'll take, so you'll have enough time, right? So you don't need to worry about that. So you make sure that there is enough time to prepare and.
Sir, just one more time, can you show the link, sir? The play source where it is.
I think it's been posted in the chat, pasted in the chat.
It's not there.
Isn't it there?
Yeah. Got it.
Okay, so let me go over this now. Okay, so I'm just wondering which is more important. I think this is more interesting also. So let me finish this part as quickly as I can. So you have seen a lot of probability distributions in week 4, right, of MLT. So we have Bernoulli, we had Gaussian, we had multivariate Gaussian and all that. So we had GMMs, right? So how do you plot these kinds of objects in Matplotlib? So wait, let's very quickly look at that. So before you want to plot something, we have to actually have a sample to plot, right? So we need to sample, say, a set number of points from a distribution. So what is that distribution here? We'll start with Bernoulli. Okay, so Bernoulli is what we're going to use. So before that, I'll introduce what is called a random number generator, because we need that to generate random numbers or samples from our distribution. So that is done as follows, right? np.random. Okay, so this is how you generate a random number generator object. So it's called a random number generator object, and we'll be using this RNG. So the way you generate 1000 points from a Bernoulli distribution is as follows. So the values can be 0, 1, right? So that is the first thing. And there is a probability associated with this, right? So P here is a parameter, okay? P that you see here is a parameter that is going to give you the probability of picking these two choices, right? So what is the probability of picking a 0 according to the Bernoulli distribution we have given here?
0.3.
Right? So this is 0.3, comma 0.7. Okay, that's the probability of choosing either 0 or 1. And we want how many samples? 1000 samples. Okay, so the whole thing together is going to be your X. Okay, let's now see what X looks like. It will look like a sea of ones and zeros. Right now, you have actually drawn a sample of 1000 points from Bernoulli of 0.7. So if you look at the shape, you will notice that it is 1000 comma, so 1000 points. You now have a sample. The best way to visualize this kind of a sample is
Probability of success is 0.7. So P should be 0.7, 0.3 or 0.3, 0.7. Okay, got it. Yeah, 0 corresponds to 0.3. I got it.
Yeah. Right. So now bar plot, right? So we look at bar plots. Bar plots need two things, right? One is they need what you are plotting on the x-axis. X-axis you are plotting 0 or 1, right? And y-axis you are plotting the number of items. Okay, so number of items, you want to know how many ones are there, how many zeros are there in X. Okay, there's a nice way to do this in NumPy. I'll have to defer this, or either one of the other two instructors will do this tomorrow. So you look at how many times one appears. Okay, so X double equal to 1 will give you the number of times one appears. So I'll just
in a real world.
So I just run this. What is happening here is there are 1000 data points, right? Now, for each data point, when I run this cell, it's going to tell me if in that particular index 1 is present or not. If it is present, it will be true. If not, it will be false. Okay, so let me take a simpler example. Let's say A is a NumPy array that looks like this. Okay, now if I ask, when is A equal to 1? That will return this particular Boolean array, right? Array of Booleans, which is true, false, false, true. Do you all get what this is? Okay, so this is one way of seeing how many ones are there. How do you see how many zeros are there? You ask this different question, right? When is A equal to 0? Okay, so interestingly, num allows other NumPy arrays to be indices. So I can do something like this. You're seeing this for the first time, it may be very confusing. So what we have done is we have plugged in the result of A double equal to 0, which was this Boolean array of trues and false. That is a bunch of values. We have put it as an index into the original NumPy array itself.
Sir, can I say something?
Yeah.
So instead of modifying in the single cell, can you make different cells so that it will be there and we can see later also? Means you are modifying in the single cell in the same cell, right? So can you make it different cell and can you show it so that it will be there and we can see later?
Okay. Yeah, I'll try to do that as much as I can. So yeah, so what I'm saying is this is A double equal to 0, and then what we are doing is we are plugging in the value of A double equal to 0 into this. So wherever it is 0, it will just return those elements to be. Okay, so I don't know if you all got this, but this is going to give me a way to find out how many zeros are there and how many ones are there.
So do we just want a count of the numbers or do we want the position also?
We just want a count.
Count we can do, for example, if you simply, I mean, there are various methods, but for example, we have A is equal to NP dot sum X will give you one,
Correct,
a number of ones.
That is correct. It'll work for a Bernoulli, but if you want, say, some kind of a categorical distribution from, say, throwing a dice and finding out, right? So there it becomes a little bit tricky. That's why I'm going.
Yeah, correct.
Okay, so what we are going to do is we are going to look at all those positions in the NumPy array where X is 1, and we are going to look at the shape of that resulting array. That will give me number of ones. Likewise, for number of zeros, I'm going to look at where all I get a 0 in my original NumPy array. That will actually give me a smaller NumPy array whose shape is, if I take the shape, that will give me number of zeros. Right, so let me just print out the n1s, n0s, and you will see that they should add up to 1000. Okay, so the 2 should add up to 1000 eventually. Okay, so all that you need to plot the bar plot now is how many zeros, how many ones.
Why, I'm sorry, what is the purpose of shape in which we are writing as 0? Does it mean something like?
So shape, see this x of x double equal to 1 will actually give me what? It will give me an array of ones, right? Wherever there is 1 in this x, original x, it will give me all those ones. Okay, I want to count how many such ones are there. So I ask for its shape. Its shape is 719 comma. So it's a tuple, right? So I want the actual
zeroth element of the tuple. Okay.
Yeah, right. So that gives me the shape. As Vasu said, here you can, in this particular case, you can just do x dot sum. You'll get the number of ones, right? But if you are looking at something that is not Boolean, that has, let's say, 0, 1, 2, then it becomes slightly tricky, right? That's why this is more general, and that's why I'm using this, right? So this is the bar plot, right? Now 300, roughly 700. So if you now increase the number of data points from, say, let's say you want 1 million data points. Okay, so if you want to sample 1 million data points, it will take slightly more time, but it will eventually work out. Right? If you run this, you will see that it's much more, the bar plot will actually be closer to 300,000, I believe, 300,000, right? So you can see that it's slightly more ideal than the 1000. So the more the samples, the closer your approximation. Okay, so that's a bar plot. Now, recall that I used RNG dot choice for the bar plot, sorry, for the Bernoulli. Here I'm going to use, simple enough, RNG dot normal. Okay, mean is 1, variance is 4. So RNG dot normal usually takes the standard deviation. So I'll put in 2 here. And I'm sampling 10,000 points, right? So 10. Okay, so that will give me 10,000 points sampled from a Gaussian distribution with mean 1 and variance 2. Okay, that's very simple actually. You can just go back. I know I'm rushing, but please bear with me. So now plt.hist, again, plotting a histogram is very simple again. So we just pass the data. Okay, it will create a histogram. This actually doesn't look so nice. So I'm going to introduce few things here. You can change the number of bins, right? By default, I think it uses 10 bins. Okay, so you could change the number of bins to, say, 100. Okay, you could do that. Okay, and the other thing that you notice is that the distinction between the bins is not very clear. Okay, so you can modify that using what is called an edge color. Let's say the edge color is black. Okay, so this is what you end up. So you have 10 bins with edge color being black. Okay, histogram of X. Now again, I want to go back and maybe make it 1 million data points, normally distributed, mean 1 and variance 4. Okay. And let me make it say 100 bits. Now, if we plot it, you get a very nice normal Gaussian bell curve, right? So notice that its mean is 1. Okay, so this is how you plot histograms. And perhaps most important thing in this series is a bivariate Gaussian. Say what we have looked at so far is a single univariate Gaussian, right? Now, what about a bivariate Gaussian? Just like you had RNG dot normal for single univariate, you have, if you want to plot multivariate Gaussians, you have something called multivariate normal. Okay, so you need 3 parameters here. First is the mean vector, right? Mean vector here is 1, 2, and that thing that you see here is a covariance matrix. Okay, if you remember, you studied this in week 8, right? Gaussian naive Bayes. So you would have seen all this. This is actually a diagonal matrix, right? Well, let me use np dot diag of 1, 5. This is a covariance matrix, and np dot multivariate normal of mu covariance matrix and size. Okay, so you have your points. Now, can someone who's still on the call tell me what do you think the shape of X will be?
X will be 2 by 1000.
Right. Yeah, it's right. It's in this case, it's 1000 by 2, right? But you are correct.
1000 by 2.
Right. Essentially, it's the same. So 1000 data points, each having 2 values, right? So it's a bivariate Gaussian, meaning it's R2, right? It's in the 2-dimensional space. So each row will correspond to 1 data point. So the best way to visualize these things is using a scatter plot. So
one question, Karthik sir, I like in a separate chat also I'd asked, and I'm still trying to figure this out very well. See, let's say there are 2 random variables XY, both are random normal. Together, that's a bivariate. And let's say I have just one variable X, but it has 2 dimensions and it's a normal, that also is a whatever bivariate normal, right? Both are treated as bivariate normal. Is that correct?
So you have to, so you could either treat a random vector of size 2 as coming from this distribution, or you could treat two scalars X, Y, which are jointly distributed as a bivariate Gaussian. I think both are the same.
Both are the same. Okay.
It's what I also think, but I am also like not 100% sure. So, but currently that's the answer I would maybe give.
Yeah. Okay. Got it.
Okay, so this is the scatter plot, right? Scatter plot, if you remember, you need the X values and the Y values. So the X values are what? The first column is the X value, second column is the Y value, right? So first column is colon, 0. Second column is colon, 1. Okay, so the scatter plot looks something like this. Now the problem is, if you look at it at this zoom level, things may not be very clear. So what I'm going to do is I'm going to zoom out a bit. In fact, there's a way to zoom out. So if I want to zoom out, what can I do? I can increase the scale of this graph, right? So there's a way to do that. So I'm going to give the limits, right? X limits, the limits of the graph here. Currently, it's like roughly from -3 to 5. I'm going to make it -10 to 10 or -15 to 15, let's say. And on my y-axis, I'm going to increase the scale to the same thing, right? -15 to 15. Now let's see what happens. Okay, notice that it looks elliptical, right? So earlier, when the scale was, when we were zoomed in, this looked kind of circular, okay? And the exact shape was not very visible. Now, when you zoom out, it looks elliptical. Now, where do you think the major axis of the ellipse lies?
It's normal to this plane, right?
Right. So it is actually in the y-axis because your covariance matrix, in fact, the variance is higher along the y-axis. That's why the major axis or the most important direction is the y-axis. Okay, so this is one. So I'll not do the estimating the sample covariance matrix part, but let's just play around a bit with the covariance matrix. So
is there a way of kind of rotating this 2D plot and give a three-dimensional view? No, right? Not in this.
Not in in this current format, right? But we can get hold of that, but not using the simple PLT dot plot. Okay, so I'm going to plot 1 million points. Okay, I'm going to sample 1 million points from a bivariate Gaussian with identity covariance matrix, right? So you'll notice something interesting here. If you actually plot this, you will see that it's fairly circular, right? So yeah, so notice that it's if you use a identity covariance matrix, it's actually circular. Now let's change the covariance matrix a bit. Let's make it positively correlated. So currently there is no correlation, right? 0, 0. If you make these off diagonal elements 0.9, notice what happens. You have a very strong positive correlation between the x and y values, right? So that's what happens. You could also do the other way around. You could make the off diagonal elements negative, okay, and maybe increase the covariance to 0.99. Okay, now you sample again 1 million data points. And if you plot the scatter plot, you will see that points are even more strongly correlated now, right? And most of the variance lies along this particular line. Okay, so that's basically what we have. Maybe there's just 10 more minutes, and I'll do this part because that will give some kind of completion to what we have seen so far. Let's do PCA on top of this data set, right? Assume that this is the data set. I'll very quickly do PCA on this, right? So that you get some kind of at least one ML algorithm today, right? So at least that much you should do. So you have the data set, which is x dot shape. It's 1 million, 2. So what is the first step that we'll do in PCA?
Center the data.
Centering, right? So we'll do centering. The way to do this is x minus equal to, you are subtracting the mean of the data set. Okay, the mean of the data set, but there's a particular axis along which you have to compute the mean. In this case, since the data points are all along the rows, okay, the data points are along the rows, this is the axis along which you want to find the mean. Okay, now we have actually centered the data set. So we'll verify that. If you verify it, you will see that the mean turns out to be 0, 0, right? So this is like 6 into 10 power minus 17, which is like 0 for all practical purposes. So this is 0, 0, right? So this is the first step in PCA, right? So we have centered it. Now, what will be the next step? So we want to compute the covariance matrix, right? Even before that, yeah, you're right. So covariance matrix, right? So it is actually XX transpose if the data is D cross N, but here my data is actually N cross D. Okay, so samples comma dimensions. So my covariance matrix will actually be X transpose X divided by N. Okay, so where N is N cross D. So X is N cross D, remember that, right? So this is my covariance matrix. The next step will be we'll find the eigenvalues and eigenvectors. So for that, we already saw this, right? NP dot lineage H. If you pass the matrix, you will get the eigenvalues, you get the eigenvectors, right? And so let's look at W1. W1 is the first principal component, right? So now we want the principal components. The first principal component is nothing but eigenvector corresponding to largest eigenvalue. That is the one of the columns of this eigenvector matrix, that is the last column. So I'm going to use negative indexing for that. So that is W1 and W2 will be eigenvector of 0. That's the first column. Okay, so I know I'm like not stopping, but I just want to show this to you and leave it at that. You can return and see what happens. So so far so good. So let's just print the eigenvalues and see what we get. So was an error. So let's run it again. Okay, so if you look at the eigenvalues, notice how the largest eigenvalue is nearly 2. The smallest eigenvalues, in this case, there are only 2 eigenvalues, but it's quite small. Do you see why that is the case? Most of the variance is contained along one direction, right? That's why it's happening. So let's go ahead and visualize the whole thing. So I'm going to carry over the scatter plot from here. So I've done the scatter plot. Let me also add an axis. So that x-axis is in black color. The y-axis is also in black color. Okay, I've added the scatter plot. Now I have to visualize my principal components, right? So how do you visualize the principal components? Any ideas, anyone?
You may want to add that line there. The E is missing in the previous.
Where? AX.
Line 18.
Oh, okay. Yeah, right. Okay, so we want to add the PCs. So the PC is what? W1 and W2 vector, right? So it's actually a straight line equation, right? It's y equal to mx. That's what you need. So for this, I'll use y equal to mx that we again saw earlier. So I'll use again 15 to 15, and I'll plot the first principal component as W1 of 1. This is the slope of the first principal component, right? Slope is y by x, right? So that is what I'm doing here. And I plot x comma y1, and maybe I give it a color of red. And then likewise, I plot the second principal component, that's y2. Okay, so y2, again, slope is W2 of 1 by W2 of 0. This is, let's say, green. Okay, now I plotted the 2 principal components. Now let's put all of this together. Okay, so they are not looking perpendicular because my graph is not square. So let me try to fix that by changing my figure size to something that is square and see if that helps. Okay, that helps, right? So the quick summary of what we have done is we have sampled 1 million data points from a bivariate Gaussian, and the scatter plot of that is these blue points. Then we centered the data set. Okay, that is the mean centering part we did here. Okay, and then we computed the covariance matrix, and then we took the eigenvalues and eigenvectors. From that, we get the first 2 principal components, and then the rest of the thing is just plotting the 2 principal components. So W1 is this red wala, and this W2 is this green fellow, right? And as you can see, the red color line is the one which has the maximum variance. Therefore, that is the one which is the first PC. Green one is orthogonal to this, and that will be the second PC. All right, so this, I hope, contains most of the things that we have done so far. Maybe one last step is adding a label to the whole thing. This is the PC1, this is PC2, and a legend to top it all. Okay, so it's taking time because we are plotting.
So this bivariate Gaussian means each data point is having 2 features, right?
Yeah, 2 features.
And
Okay, right. So I guess creating this legend is taking some time. So yeah, that's
What have you written in line number 1, sir? We change certain parameter to make it square. This one.
yeah. So the entire figure has some shape, right? So I want this figure to have a dimension of 8 cross 8. Right. So let me remove this legend for whatever reason it's taking time. So right, if you change this,
Sir,
yeah.
sir, can you explain why you had that semicolon after the legend?
So you see the semicolon suppresses the output, right? So for example, here I'm plotting this, right? So the plot has some this method has a return value.
Yeah,
Okay,
yeah.
so I don't want the return value to get printed. That's all. So if I add a semicolon,
Okay.
whatever return value is there for the last line of the cell, that will get suppressed. Okay, that won't get printed.
Yeah, got it. Thank you, sir.
You were saying something about first line, sir. First line.
Yeah, this is the size of the figure, right? So if I change this to say 15, 15, that will make this whole thing look even more bigger. Basically, it controls the figures. Right?
What is that parameter or function which you are typing?
RC params.
Okay.
RC params is a dictionary, right? So plt.rc params. See, this is configuration parameters. If I'm not wrong, I don't know exactly what RC stands for, but it controls several things. For example, it controls font size. So if I want to change the font size, right? So where is font size? Font size, right? So current font size is 10. Now I want to change it. So I can change it in the following way. It's a dictionary, right? So you can update the values.
Okay.
So I can, let's make a font dot size to be say 20. Right. So make note that current font size is small, right? Now if I run the cell, your font size will appear slightly bigger. Right, font here meaning the title's font size, the values of these ticks, all that will become bigger. Okay, so I think we'll have to stop here. I'm sorry for going fast because see that's the nature of the workshop, right? If it were a normal live session, I could have gone a bit slow.
We have covered 4 files, right, sir? 4 files or 5?
We have covered roughly 4, right? 4.
Yeah,
I
four,
wanted to do a GMM also, but we don't have time. So,
Karthik sir, can I ask a question, sir?
Yeah.
So it is not related to this thing, but it is related to NumPy. Sir, I know in the pandas, if we do, we want to give the data to any algorithm, whether it is the probabilistic or any other linear regression, logistic. So we have to convert that data set into the matrix form. And for that, we can use a NumPy also, and there is a shortcut in pandas that is known as dot values.
Okay.
Okay, sir. So my question is that, sir, actually, I am using also the PySpark. Sir, is it possible to convert the PySpark data frame into the NumPy array or matrix form? Stack Overflow or over there, I'm not able to find the things.
Okay, so I am sorry, right? I am like really not familiar with that. So
okay, it's okay.
Someone else from the team might know. So or you can someone in Discord, if you can ask, they'll surely be knowing.
Okay. I will do that.
Okay. Yeah.
Okay. Yeah. Thank
hello, sir. Could you show on the graph like what exactly are the diagonal elements of the covariance matrix in the multivariate Gaussian showing exactly like?
So see the shape of a multivariate Gaussian is in general an ellipse. Okay. So if you don't have off diagonal entries, it means that your x and y values are uncorrelated, right? If the off diagonal entries are 0, then you have so it means that your
yeah, that I got, sir. But like 1 and 5, like in that example, like how do they affect the curve?
The diagonal entries, you mean?
Yeah.
Okay, that controls the variance, right? So for example, let's take let's change this to 0 and 5, 0, right? So if you now plot this, you will notice that the variance along the second direction is, in fact, this is so, they're like so steep, but yeah. So let me change the size. If I don't do that, it won't be clear. Okay, so let's go back to something smaller. Here we go, 5 cross 5. Okay, so this is still elliptical. Okay, once again, this is like I have sampled maybe too many points, so it's like all appearing as a straight line. Let's go with something smaller.
Sir, I think you wrote the second array in reverse. 0, 5, I think it should be.
Okay, okay. That's why it's saying it's not positive, right? Yeah, thanks. So it should be okay. Right. So see here, what is happening is you see that the ellipse is actually the direction is the usual x and y axis, right? So the x-axis is one axis of the ellipse and the y-axis is another axis of the ellipse. Now, because the second diagonal element is phi, the variance along the y-axis is higher than the variance along the x-axis. So you see that it's more elongated along the y-axis than the x-axis. That's the only thing that the diagonal elements are conveying.
Okay.
Right. In fact, if you run PCA now, it will.
Did some modification or what, sir?
Yeah. So if you, in fact, if you run PCA, you see that the first principal component is along the y-axis. Second principal component is the x-axis.
Right.
Yeah.
Okay. And the number signifies by how much it's varying, like magnitude.
The variance, right? Yeah. The phi gives you the variance of the data points along the red line, the first piece.
Okay. Then you did some modification in data or what, sir? Because it got changed.
I made the covariance matrix diagonal. Earlier it was non-diagonal. Now I made it diagonal. Right, that was the only change. Okay, so anything else? If not, I think we can close the session.
Sir, I have a thought.
Okay, in what?
Sir, I have a small query. While printing, we are getting array of list, right? Not here. The previous collab notes, we are getting array of the print is not coming like complete. It's not like a matrix or list. It is giving array of something, array of that matrix. How can we remove that array in the output?
Okay, that's a good point. So, see, if you want to remove that array, you can just directly print it. So, for example, let's say you have x equal to np dot array of, and you want to remove this, then you just do print instead of just typing out x.
Okay, there is a difference between these two.
Yeah, yeah.
Okay, thank you, sir.
Yeah. Okay, so I think we'll.
Sir, I think all the slides will you send it in the mail?
Yeah, I will. So see, the point is, I didn't complete the slides. I have some more. In fact, I need to discuss these. There are a bunch of, in fact, applications, use cases, and all that. So once we discuss that on Saturday, I'll upload the whole thing. Okay. Yeah. So anyway, thanks all for joining. And
I have one question. I just have one question. This OTT, is it mandatory that we register for this workshop, or without registration also we can take the OTT? The exam.
I'm not sure if they are independent or not. I'll have to check that with the team.
Kindly check, because as I mentioned, I missed it because of this travel related thing.
Did we
Now
get
back to
any?
take this.
Sorry, Ravi, and the rest also. Did we get any invite for the OPE? No, we
Yes.
didn't, right?
It will be given later.
We have not got
Not
any.
yet.
no registration yet, right? So, okay.
Yeah. No information has gone out from our side. So yeah. Anyway, so
Okay.
thanks.
Thank you, sir.
Thanks for joining. Yeah, we'll meet again.
Thank you.
Thank you, sir. Good night.
So where you
Good
upload
night.
these files, it is on the Google Drive or you provide the link on the Saturday?
I will the YouTube link or the
No, no,
slides.
yeah, slides and the video that you showed that you said that you'll provide after on Saturday.
Yeah, that I'll upload to the same folder, that tiny.cc.
Okay.
Yeah.
Got it. Yeah, thank you, Karthik sir.
Karthik sir, any chance we will, I know it's a little late, but any chance of just discussing some key problems from the MLT final exam, just some key problems?
Right. So may not be today, right?
No, not now. Anytime before the next term starts.
Yeah, that we can do. Yeah,
Before, because
So
some of
workshop
us will
also is
probably, because some of us will probably take MLP, and so it's good to round off the concept.
Yeah, sure. Yeah, we can do that.
Thank you, Karthik sir.
Okay, thanks,
Thank you.
Karthik sir.
Thank you.
Thanks, everyone. Guys, see you tomorrow. Bye.
Yeah.
Good night. Bye.
Thank you, sir.
Bye everyone. Bye.
Yeah, thank you, sir.